Hello, everyone. Good morning in America and good afternoon in Europe. I am Yuriko Pitones, professor of the Mathematics Department of the Metropolitan Autonomous University in Mexico. It's a pleasure for me to welcome you to this event, which personally has been fundamental achievement in my professional career, because this represents another step in the effort to bring high-level mathematics to the mathematics community of Latin America and the world, in particular to young Mexican students. I certainly believe that these events, like this conference, can change the vision of young students and potentiate academic opportunities for their future. The Satellite Conference was born in May of this year in a Facebook conversation, and we had been working for 3 months to make it a reality today. We managed to bring together 9 members of the scientific board, 17 invited speakers from 10 different countries, and around 550 registered participants from at least 30 various countries, at least. These numbers represent the impact we have had around the world. Thank you, team. This conference will not be possible without you. To continue, I'm going to introduce the members of the organizing committee and ICM-AM board. First, John Caicedo. He is PhD student at University of Osnabrück, Germany. Marlisha Sandoval Miranda. She holds a position as professor of the Mathematics Department of the Metropolitan Autonomous University in Mexico. Duban Cardona, FWO postdoc fellow at Ghent University, Belgium. He is president of the scientific board of ICM-AM Latin America. Now, I will pass the word to Marlisha Sandoval Miranda.
Thank you so much, Yuriko. And dear colleagues and students, it's a pleasure for me to be part of this satellite conference as part of the organizing committee and the board of the ICM-AM project that arose in 2020 for the first time, like the International Conference, Multidisciplinary Aspects in Mathematics and its Application, as an effort to involve Latin American mathematicians around the world in an event where converge current research in various topics and top-level mathematicians around the world working on those topics. I thank our colleagues of the ICM-AM Latin America project for this invitation. Thank you so much. And I would also like to thank all our guest speakers as well as the researchers on the scientific committee for their time in agreeing to join us for these 3 days with fascinating lectures on current topics in algebra, combinatorics, and number theory. From Mexico and the Department of Mathematics of the Universidad Autónoma Metropolitana, as well as the Tardes de Café y Algebra, our seminar in Spanish of the algebra area of our university, UAM Campus Ixtapalapa. We thank everyone for their time and attendance. Thank you so much, and I'm sure this will be rewarding for everyone. Thank you. Duban?
Thank you, Marlisha, for your work. Now we will listen to Duban Cardona.
Hey, ladies and gentlemen, esteemed colleagues and fellow mathematicians. Mexico has an immense cultural wealth, known as the homeland of literary giants like Octavio Paz and Carlos Fuentes. It played a prominent role in the cultural phenomenon known as the Latin American boom, which also includes celebrated writers like the Colombian Nobel laureate Gabriel García Márquez, the Peruvian Nobel laureate Mario Vargas Llosa, and the Mexican writer Juan Rulfo. The Latin American boom allowed our continent's writer a global credential signifying that being a Latin American author meant being on par with the greatest literary figures. Today, drawing an analogy between literature and mathematics, I feel a similar sentiment. I believe strongly that Latin American mathematicians are now widely respected worldwide for the quality of their mathematical research, their efforts to foster gender equity in academic discussions, and their commitments to inclusivity in underrepresented communities. It's highly inspirational to see different Latin American mathematicians moving the frontiers of significant advancements in mathematical research and creating opportunities for our younger generations. ECMA en Latin America emerged in Colombia in 2020 at Universidad del Valle in Cali. After finding several colleagues in Mexico, Brazil, and Argentina, all dedicated to advancing mathematical research in the region, it has been expanding throughout Latin America. Today, ECMA in Latin America is dedicated to promoting the visibility of young researchers, providing them with opportunities to engage with specialists across various mathematical fields, and working for the recognition of women's contributions to mathematical research in Latin America. The newly formed Gender Equity Commission will be led by Yuriko Pitones, who has coordinated this team of organizers for this conference. Lastly, I would like to express my gratitude to Yuriko Pitones, Marlicha Sandoval Miranda, John Vladimir Caicedo, and Luis Agustín Cárdenas for their outstanding work in organizing this remarkable opportunity. I also would like to thank to Arturo Tapias. I also like to extend a special thanks to the Universidad Autónoma Metropolitana for the generous support for our initiative. I also thank all the members of our scientific committee and also our team of speakers for accepting our invitation. Thank you, and let the Satellite Conference on Algebra, Combinatorics, and Number Theory 2023 be a beacon of inspiration, knowledge, and progress in the world of mathematics.
Thank you very much for your speech. And to finish with this opening, I want to say that I hope that this conference represents a great mathematical experience for everyone. And you are all welcome to the first edition of the ICMAM Latin America Satellite Conference on Algebra, Combinatorics, and Number Theory. Thank you so much.
Good evening, everyone. Buenos días a todos. Quizás buenas tardes, depending on where you are joining us from. But it is a special honor for me to be the first announcer this morning because I get to say hello and welcome to ICMAM Latin America Satellite Conference on Algebra, Combinatorics, and Number Theory 2023. I wish everyone a very successful conference experience. And it is my great pleasure to begin by introducing our first speaker this morning, Professor Beth Malmskog from Colorado College. And she will be talking to us about locally recoverable codes from algebraic and geometric structure, ideas and examples. Professor Malmskog, please go ahead.
Well, thank you so much for the introduction. And I just want to say thanks to everyone who organized this conference. I'm tremendously honored to be here. And it's such an exciting event. I can't believe that I get lucky enough to give the first talk here. So thank you very much for giving me this opportunity. So I'm going to speak today about something that really combines combinatorics, number theory, and algebra. So it really does all of the things that we are looking at today. But I'm going to start by introducing error correcting codes, which are maybe part of combinatorics, but maybe not the part that people are most familiar with when they're coming from more of a number theory or algebra background. So my goal today is for especially the first part of this talk to be very accessible to students. And if there's any questions, if you would like to take a minute more to look at something, please stop me at any time. I have the chat open, so I can try to respond, but please also feel free to raise your hand and I'll try and answer questions during the talk or at the end. Okay, so let's just jump in. I also want to say that this work that I'm going to speak about today represents a lot of wonderful collaborations. And so I'd like to thank all my collaborators, and I'll try and credit them as I go through. But there are so many wonderful people working in this area and coming up with great ideas that I couldn't possibly credit them all. But I'll try and reach out to the ones who have worked with me, especially in this work. Okay, so today we're going to talk about codes. And the main idea of a code is that it's just a system for communicating information. And the idea is you have to use something to communicate. The alphabet is just whatever set of symbols or actions you might be thinking about that could be used in the system. So for example, if we're thinking about semaphore, the positions of the flags would be the symbols. But in Morse code, the symbols would be things like dots and dashes. Okay. Now, of course, you probably have guessed we're not going to be talking about those kinds of codes so much. We're going to be talking more about digital codes, which we'll dig into in just a moment. But the idea with this information is that you'd like to communicate it somehow. And so the codes that I'm going to focus on today are going to be mostly focused or mostly motivated by storage applications. So the idea of storage is that you're sort of communicating with your future self or future others that will someday access your information, be it stored in a book, in a disk, or of course on your computer, or in the cloud, which is really where these applications are most motivated. Okay, so digital codes are, of course, taking a digital format information or translating your data somehow into a stream of digits. Okay, so the collection of meaningful vectors or streams of digits are going to be called code words. Okay, so when we think about a code, we can now sort of narrow that down to a set of code words. And the idea is that somewhere there's a code book. Maybe it involves mathematics. Maybe it's just something much simpler like I've depicted here. There's going to be some way to translate some message into a stream of digits. And there's a finite set of messages that you might be able to send this way. In the ASCII code chart I showed above, the idea is that you could really send any message that you could translate into the symbols on your keyboard through the ASCII code just by combining code words into sort of larger words. And that idea exists in coding theory in general too. Okay, so now that we have sort of a first glance at codes, which ones are we going to focus on here? Well, of course, they're going to be a little more mathematical. So we're going to look specifically at linear codes. So a linear code over a field FQ where Q is a power of prime, and we're looking at the finite field with Q elements there, of length n is just a subspace of fq to the n. Okay, so we're looking at vectors over fq of length n. Now, a couple of interesting things that we use to talk about codes are the distance of a code. Okay, so let's just start by defining the Hamming distance. The Hamming distance between two vectors is just a number of positions in which they differ. Okay. So now the Hamming weight of a word is going to be, or of a vector in general, is going to be the number of differences between that vector and the zero vector. So the number of non-zero entries in the vector. So if we're looking over a whole code, that's a large, a collection of code words. The minimum distance of that code is going to be the minimum distance between any two non-identical code words in the code. And because it's a linear code, you can do a quick exercise for yourself and realize that this is going to translate into the lowest weight of any code word besides zero. So the minimum distance of a code both says something about the number of differences between any two code words and the number of non-zero entries in the lowest weight word that's not zero. Okay, so why is distance interesting for a code? This gets at the whole idea of why we would think of these linear subspaces as being codes. The idea is that these are going to allow us to correct errors. So if we receive a transmission of a vector, which was not a code word, then it's probably started as a code word, but some errors occurred. Okay, so the idea is if some errors occurred, we can think of those as creating, each error creates a Hamming distance of 1 between the original code word and the transmission. And so if we didn't have more errors than just under half our minimum distance of our code, then we're going to be able to make a pretty good guess at the original code word. So the idea is if the minimum distance is d, and the distance between the transmission and some code word is less than or equal to d minus 1 over 2, then probably the intended code word was v. And so we can use that to fix the errors in W and understand the actual intended transmission. Okay, so now if there's more errors than this, of course, we would be guessing wrong. But the idea is that you figure out what kinds of errors your channel is likely to have, and then design your code so that it's going to be able to fix as many errors as you're likely to see most of the time. In this case, like, as I mentioned, you can correct the floor of d minus 1 over 2 errors. But in fact, you could detect, as in know that there had been an error for up to d minus 1 errors. Because if you had d minus 1 or fewer errors, you would be you wouldn't have actually been able to transform into another code word. And so you would at least know there was an error, and perhaps you could ask for retransmission. Okay, so what makes a code good? Well, for linear codes, there's the singleton bound, and there's also, if you're interested in nonlinear codes, there's an analogous idea there. Okay, so since a code is a linear subspace, we have discussed what the length is. The code also has a dimension because, every linear subspace is going to have a dimension. And so let's say you have a code of length n, dimension k, and minimum distance d. Then it turns out that d must be less than or equal to n minus k plus 1. The idea here is that there's a trade-off between the dimension, meaning the number of code words that you're able to have, and the minimum distance, meaning the number of errors that you're able to correct. A code that meets the singleton bound is doing as well as possible in the trade-off between those two items. And it's got a special name, a maximum distance separated code. So in some ways, this bounds the number of errors that can be corrected. If you solved the opposite way for the dimension, it would bound the sort of number of code words. And one way that you could think of that would be bounding the efficiency of your code. Just to look at this again, we could consider R, which is determined by k over n, that is the dimension over the length of the code. We call this the information rate. And the idea is that if the dimension is large in comparison with your length, then you're not transmitting too much extra information. That is, your code is efficient. So you would like R to be as large as possible, close to 1, if you could have it. Now, delta, which is defined by D over N, is what we call the relative minimum distance of the code. Now, since D bound is related to the number of errors that you can correct, this is going to be a measure of how effective your code is, how many errors it's able to fix relative to the length of the code. And you would also like this to be as large as possible if you could. So if we plug these in, if we kind of divide the singleton bound by n, we see that a code that meets the singleton bound will have r plus delta equal to 1 plus 1 over n. And so we can also kind of think of these relative quantities if you're interested in those things. Okay, so we want codes. We want them to be efficient and effective. Let's dig in a little deeper on this. So the example, I think the most important example of this talk, and probably one of the most important examples of codes in general, is the Reed-Solomon code. And so basically what you're going to do is take a finite field, and you're just going to write down the elements of the finite field and choose some ordering on them. Okay, so we're going to call them alpha 1 through alpha q minus 1 in this case. Then you just choose some k between 1 and q minus 1. Okay, and you're going to let L sub k minus 1 be the set of polynomials with degree at most k minus 1. Okay, so this is a linear space. Given a polynomial in this space, you're going to create a vector by just taking the polynomial and evaluating it at each of the points in your set. Each of those, I call them points because I think of this geometrically, but they're really just values in the field. And so you evaluate the function at each of the values in the field, that becomes a vector. And those are going to, in fact, be the code words for the Reed-Solomon code that we denote by RSKQ. Okay, so if we think about this for a second, here's a picture of Reed and Solomon, Gustav Reed and Irving Solomon, I believe, who invented these codes. So the interesting thing to note here is that L sub k minus 1 is a k-dimensional vector space over FQ. And the evaluation map, as long as we make k smaller than or equal to q minus 1, this is going to be an injective map. And so we end up with the linear space being isomorphic to L sub k minus 1. So that means the code RSKQ is a linear code of length q and dimension k. So there are q to the k total code words because we have dimension k. And if we think about the minimum distance, this is actually not too hard to reason out. How many zeros can a polynomial of degree at most k minus 1 have? Well, k minus 1 zeros. And so if we think about the minimum distance as instead the minimum weight, we've got q entries and we can have at most k minus 1 zeros. So the minimum distance is q minus k plus 1. Okay, well, this is great. This actually is the singleton bound of n minus k plus 1. And so Reed-Solomon codes, first example we look at, turn out to be as good as possible. So great, we found our maximum distance separable codes. Life is good. Okay, so let's just look at a quick example. And of course, I have a picture of Saturn here that is from the Voyager space probe. The Voyager probe used Reed-Solomon codes to transmit these photos back to Earth. And so it's a, sort of an illustration of the power of the codes. So just to give you a quick look at this, if Q was 7 and K was 4, then our entries would just be the numbers 1 through 6 when we're looking at the integers mod 7. And we could take a basis for our space as just the polynomials 1, x squared, and x cubed. By evaluating those polynomials at each of the points in our list, we get first the all ones polynomial, then the x polynomial, x squared, and x cubed. And those vectors are going to be a basis for this Reed-Solomon code. So it really is just that straightforward, and it's pretty exciting. Okay, so great, we solved all our problems, right? Well, it turns out no, that even though we have found these polynomials or these codes which are in some sense as good as possible, there's a small problem. And that is that the length and the number of code words are restricted by the size of the field, right? Because the dimension of the code has to be less than the length of the code. And the length of the code is just the number of elements in the field. So if you want longer Reed-Solomon codes, like more code words that you can use, you're going to need to work in a larger field. But that's kind of a drag because there is a trade-off when you move to a larger field. It's going to slow down computations, or it's going to eat your memory. And so you would like to work over a small field if possible. Okay, well, here's the first, or one of the big ideas, not my own, that take this talk somewhere interesting. You could actually use varieties over finite fields to find codes over FQ that are both efficient and effective, like Reed-Solomon codes, or close, but have longer and more code words. So the idea is, instead of just using the non-zero values in the field, you could take a curve or another variety over that field and use the points on that curve or variety as the evaluation points for your code. Okay, so of course, now instead, we can't just use polynomials anymore because we have a more complicated set of points. So we're going to use some, I'll just say, clever space of functions on the variety. And there's been a lot of different ideas of clever spaces of functions. So let me just kind of give you that general picture. Oh, sorry, one second. Yeah, so what kind of curves might we want? This is my moment to slip in a little bit of curves over finite fields, which I love. Okay, so we would remember, the idea is that we would like to have curves or varieties that have more points than just Q over FQ. So what we'll do is look for curves with as many points as possible, or close to as many points as possible, or again, maybe move to a higher dimensional variety. When we're focusing on curves, though, one important aspect of the curve that will limit the number of points it could have is its genus. So the genus of a curve, as many of you may know, but especially students might not, the genus of a curve is a measure of the curve's complexity. If you're looking over the complex numbers, the genus is going to just be the number of holes in the Riemann surface. But you can actually define this algebraically too, so that it works over the over finite fields or positive characteristic, and it's going to be the dimension of the linear space of one forms. Now, we're lucky in that we're going to be thinking mostly of smooth plane curves, and these are easier to find their genus. We just can use the Plucker formula, which says the genus really depends on the degree, as we've seen here. Okay, so why do we care about the genus? Again, it has an impact on how many points a curve can have. So the number of points a curve can have is bounded. It's about Q plus 1 points, so the Q values in a field plus 1 for a point at infinity, plus or minus this factor 2g root Q that depends on the genus of the curve, the complexity of the curve. Now, we want more points, so that we'll have longer and hence maybe more code words. And so we're going to be looking for curves that are close to maximal, which is what we call those that meet the upper bound here. Okay, so let me give you an example. The Hermitian curve. This is my favorite curve. It's given by y to the q plus 1 equals x to the q plus x, and I've written the projective homogeneous model below it. This is a smooth curve and irreducible with 1 point at infinity. If you check, its genus is q times q minus 1 over 2. And the most exciting thing about this curve, maybe one of the most exciting, is that it's maximal. It has q cubed plus 1 points over fq squared. Now, if we had a lot of time, I would explain how this works, because it's really quite straightforward. The thing that you'll notice is that if we're looking over fq squared, the left-hand side here with y is the norm map from fq squared to fq, and the right-hand side is the trace map from fq squared to fq. So it turns out that these, looking for places where the norm of one value equals a trace of another value yields a lot of combinations. And it's not too hard to actually count up q cubed plus 1 points on this curve. Okay, so that is maximal if you checked the Hasse-Weil bound from the last slide. And you can actually prove that this is the maximal genus for a maximal curve over this field. So in some ways, it's like as maximal as you can get. And it also, as it turns out, has extraordinary symmetry. The automorphism group of this curve is as large as possible. It's the unique curve with this large automorphism group. And it's on the order of 16 times the genus to the 4th, which is sort of amazing. Now, one other important point about this curve, which I will be using in a few slides here, is that every line intersects HQ, the Hermitian curve, in either 1 or q plus 1 points. And so it has an amazing regularity of intersections as well. Okay, so there's an example of a curve that we might be interested in with its parameters. Now, how do we turn it into a code? So given a projective variety defined over some field, we're just going to do something very similar to what we did for Reed-Solomon codes. We're going to choose some points, leaving one out so that we can have poles somewhere. But for now, you can just think of P1 through Pn as being some points on the variety. Now, then we will define some set of functions in the function field of that variety. And for each function, we're just going to create a vector by evaluating that function at each of the points on the evaluation set. Now, we will choose some linear space of functions on the variety that doesn't have any poles in the evaluation set. And we can just create what we call an evaluation code, mimicking Reed-Solomon by doing exactly that. We take the functions, evaluate all of the functions in the linear space L and evaluate them to create vectors on the evaluation set A, and that's our code. Okay, so if we apply this idea to the projective line, and the points are really just the affine points, that is the non-infinite points on that line, those can just be captured by the values in the finite field. And so if our linear space is polynomials of degree less than k, then really what we're getting is just the Reed-Solomon code, as I mentioned earlier. This is just a generalization of that Reed-Solomon code. Okay, so now if we take the points on if we consider now the Hermitian curve that I just described, and you look over the field FQ squared, and you use this linear space of functions, which are defined, they're two variable functions now because it's a curve, but they have the space has a fairly simple definition. Then the idea is that if you take, for your evaluation set, all of the points on the curve besides the one at infinity, then the evaluation code that you get is called a 1-point code on the Hermitian curve. And it has length q cubed because that's the number of points minus the one at infinity. And then the dimension is given by m minus g plus 1, or it's at least that. And so the notion is that m is a parameter that you've chosen up here in the vector space that just basically bounds the degrees of x and y in your function. Okay, so the minimum distance then can also be bounded using geometric ideas to be at least n minus m, okay? So this code is not exactly as good as a Reed-Solomon code because of this minus g factor that you see in the dimension, but that's just a fairly minor defect, and otherwise the code has very good bounds on its parameters, so it's pretty exciting. It's also very long. It has q cubed instead of q squared points, which is if you took the Reed-Solomon code defined over fq squared, you would be stuck with words of length at most q squared. Okay, so now nodding towards where we're going next, you can also use higher dimensional varieties. If the variety is just projective space in m dimensions, and you take the evaluation set to just be the affine points in that world, and your functions to be just m-variate polynomials of bounded total degree at most v, then the evaluation code you get there is called a Curie-Reed-Muller code. And we denote it by RMQVM, as you see there. And the idea here is that this is just sort of the higher dimensional analog of the Reed-Solomon code. Okay, so there's your basic introduction to algebraic geometry codes. Now, let me just give you a little more motivation. I said we wanted codes and we wanted them to be efficient and effective, but what if you wanted to do something else? Maybe you want to store your information in the cloud. What could possibly go wrong there? Oh, I do see that I had a question a minute ago. Let me just go back to Diego's question. Why are we removing the point PS? The idea is that you were removing the point PS so that you didn't evaluate all the points on the curve, just so that you would have some place for your functions to have a pole. Because every function has to have a pole somewhere. If it's a polynomial, that pole is at infinity, and so we would throw out the pole or throw out the point at infinity. But if you wanted to use that point at infinity and use rational functions, maybe you could throw out a pole somewhere else where you allowed those functions to, or throw out a point somewhere else where you allowed those functions to have poles. Thanks for your question. Sorry, I didn't answer that more at the moment. Okay, so back to the cloud. What could go wrong in the cloud? Well, as you can imagine from these pictures, everything could go wrong in the cloud, right? We've got our information stored in these banks of servers. And as you can imagine they generate a lot of heat, and this is just like an industrial scale thing. And so bad things happen all the time. Servers will crash and become unavailable. Maybe they'll actually start on fire. All kinds of terrible things can happen. It could also happen just that a particular server is like being accessed by millions of people at once. And so it's unavailable to additional requests. And so you may just want to be thinking about it that way. Okay, so the idea here is that instead of storing your information just on one server, which would mean that if that server crashed or became unavailable, your information was just completely inaccessible. What you'd like to do is actually spread your information across many servers. And in the way of thinking about this, what you could imagine is you have a code word that is your information, and you're going to store one position of that code word on each server. So if you have n servers, then you would store one position of your code word on each of those servers. And now this is clever because it means that if one server crashes, then you can use the information from the other servers to determine what the one server had on its what that one server had stored. And so the notion here is that if you do this, like you have a code word that's stored across many servers, you could theoretically access all those servers in order to restore one down one. But these code words are perhaps very long, and you would like to avoid that situation. So what we'd like to do is have a small set of servers, perhaps nearby the one that has crashed, so that if the one server crashes, we can restore the information by looking at a small subset of other servers. Okay, so this is the motivation for locally recoverable codes. A code C is said to be locally recoverable with locality R if any erased code word symbol can be recovered by accessing at most R other symbols. And ideally, you'd like R to be fairly small, smaller than the dimension. The set of the symbols that are used to recover that symbol are called the recovery set for the ith position. And we would like to understand codes where every position has a recovery set and maybe even more. Okay, so this is a locally recoverable code, and we'll talk about some of those shortly, but of course I'm demanding, right? I always want more. And so let me just motivate that. One way that you might think about these local recovery sets is by grouping the symbols into some subsets like we see here. And the idea is that if one of those positions is erased, then you can use the other positions in the same set to recover it. Okay, well, that's great as long as just one is erased, but what happens if two are erased, right? If two symbols become unavailable at the same time? Okay, then we may not have enough information to recover both, so it would be handy if we actually had a different way to recover each of them, okay? So this is the notion of availability. A locally recoverable code with T recovery sets for each symbol is said to have availability T, and that's denoted as an LRCT, just for going forward. Okay, so just to give you one more idea here, as if I haven't asked for enough already, another idea you could use in trying to recover additional erasures is hierarchy. Now, the notion here is that instead of having several disjoint recovery sets, you might have, as we see depicted here, sort of small recovery sets. But if you have additional erasures, you may have these small recovery sets nested into larger recovery sets where we can recover more erasures within those sets. Okay, so you can see here that two of the small recovery sets have been grouped together. And this is like a slightly larger recovery set that can maybe even recover more erasures. For example, maybe even all four of these. So if we organize these recovery sets in a nested way instead of in a disjoint way, then these are going to be called hierarchical locally recoverable codes. So you can have a lot of layers of hierarchy. You can imagine this can get very complicated, but the idea is not too complicated. Now, we can combine it with availability and potentially even have availability each level. Like, there are so many possible combinations of things here. And so my goal for the rest of this talk is really just to understand how locality, availability, and hierarchy can arise naturally from geometry and algebra, as we are going to see going forward. What are the possibilities of this idea, and what are the limitations? Okay, so there's one big idea that powers the whole rest of this talk, and that is the idea of polynomial interpolation. So this is a fact that many people probably, even though it may be early in the morning, depending on where you are, will recognize as familiar. But that is that a polynomial of degree at most m is fully determined by its values on any m plus 1 inputs, right? So a parabola, that is a quadratic function of x, is going to be determined by any 3 points, as we see here. So the idea is that you can use this fact to locally recover Reed-Solomon codes. So if any position is erased, right, remember we're dealing with if it's RSKQ, we're dealing with a polynomial of degree k minus 1 or less. But if a position is erased, that means we don't know the value of f of x for some x. But we can use the values of f of x for any k other values, any k other x's, to actually interpolate the polynomial f and then repair the erasure by just plugging in our value that is where our code has been erased into the polynomial f that we've worked out. So this idea just involves some linear algebra and a cup of coffee, but it turns out to be really, really powerful in this context. So it's clever and it's easy, but for Reed-Solomon codes, it's actually a little bit of a drag because the locality, that is the number of positions you need to access to recover one, is the same as the dimension of the code. So you don't really have anything extra going on that gives you interesting locality here. Okay, but if we apply this idea to Reed-Muller codes, we do start to get something pretty interesting. So the Reed-Muller code 523, so that, remember, is over the field F5, and it's going to be two-dimensional, and we're going to look at polynomials of total degree at most 3. Okay, so this is my cartoon of the picture here. The 25 points that you see are the evaluation points, that is the points in the plane over F5. And we're going to be evaluating polynomials of total degree at most 3 over F5. Okay, now these are 2 variable polynomials, so interpolation is a lot more complicated. And we're not going to directly try to interpolate here. What we're going to do is imagine restricting each of these functions to a line. Now, a 2-variable polynomial restricted to a line is going to become a 1-variable polynomial in whatever parameter we use for our line, say t. Now, that polynomial is going to have degree at most 3 because that was the total degree of the polynomial. And so we're going to be able to use the points along, since there are 5 points on any line. If one is erased, then we can use the other 4 points on the value of the function at the other 4 points on the line to interpolate the degree 3 polynomial that we get when we restrict to that line, and use that to find the missing value of the polynomial. Now, this is wonderful because, in fact, we have many recovery sets for each position. We have high availability. Every line through that point is a recovery set. Okay, this is wonderful, but the one issue is that it does have a low rate. So we don't get a ton of functions in a standard Reed-Muller code. Okay, well, it turns out there's a really clever idea, and I've worked with collaborators on extending this idea, but the original idea was not mine at all. It's called lifting. And this idea was introduced by Guo Kaparti in Sudan in 2013 to increase the rate of the Reed-Muller codes that we were just looking at. Okay, so the idea is that you take some evaluation code of short length and lift it to a longer code by basically you're thinking of this within some linear world. And if you have a linear evaluation code, the short one, you want to lift it to a larger linear world by requiring that every a large code word must have the property that anytime you restrict it to a smaller linear variety, you're going to get a code word in that short code that you've chosen. Okay, that sounds very complicated, but basically the idea is that you want to think of geometrically of the evaluation set for Reed-Muller codes, where along every line, the code word must restrict to a Reed-Solomon code, okay? So another way to think about this, which I think is the clearest, is that there are some multivariate polynomials that have high total degree that actually reduce to low degree polynomials on all the FQ points of rational lines in m-dimensional space. So this had been observed earlier, but I don't think people really realized how many such polynomials there were. So what you're basically doing is taking a Reed-Muller code, which, as we said, has low rate, and then you're boosting it by including all of the functions of high degree that, when you limit them to lines, have low enough degree that you can use this polynomial interpolation recovery method. Okay, so let me just give you a quick example to show you how this works. If we have a monomial, as described there, and some line parameterized by alpha t plus beta comma t, then when you plug the line parameterization into the monomial, you get a univariate polynomial, and it'll have degree at most q minus 1 after you reduce it. Okay, so now we're going to say the monomial is good if the degree is in fact at most q minus 2 after reduction for all alpha, beta, and fq. Okay, so what am I getting at here? The idea is that each line in fq has q points on it, and if we erase the value of this polynomial at one of the points, then we're going to have q minus 1 left. And so we would like to find a function. We would like to include all functions that can be recovered, even if when one position is erased. So we've got q minus 1 points. That means we need our polynomials to, on lines, reduced to degree at most q minus 2. So now, for example, if q is 8 and m is 2, now we look at the monomial y to the 6, x to the 6. This has total degree 12. So like it doesn't work a priori as a function that we could recover on lines, because we would need, since q is 8, on lines we can only recover polynomials of total degree maybe at most 6. But you see here on the line x equals t, y equals t, when we plug those values in, x to the 6, y to the 6 becomes t to the 12th. But because we're working over f8, this is actually going to be t to the 5th. Okay, and so that actually works out. That's a polynomial we can interpolate on lines. More generally, you can take this and work on any line with the coefficients alpha and beta, and through doing a little bit of slightly annoying but not too bad multiplying, you will find that the polynomial you get, or by restricting the monomial to the line, is given here. And then again, applying finite field reductions, we get a polynomial that has degree 6, which is something that we can interpolate given 7 values on a line. So there's 28 monomials with total degree at most 6, but in fact we get 37 good monomials when we actually include all these new ones. And so there's a lot. And it turns out that as your field grows, so if q equals 2 to the h, as h goes to infinity, your rate actually approaches 1, which is, pretty amazing. This is a great boost from what we had before. Okay, so the first big idea I'd like to share here is the local recovery of Hermitian codes using lines. So you can think of those one-point Hermitian codes as punctured subcodes of the Reed-Muller codes and kind of use the same idea there. Basically, think of them as existing in the plane and then apply the same ideas of using line recovery to those codes. So the way this works is the following. So for any point on the Hermitian curve, you're going to have q squared distinct lines through that point. Well, you actually have q squared plus 1 for each slope plus the vertical line, right? But then we're going to throw out the horizontal line and we're going to throw out the tangent line, okay? And what we're going to end up with are q squared minus 1 lines passing through each point that intersect the curve in exactly q plus 1 non-infinite points. Okay, so remember what I was saying about the Hermitian curve. It has this amazing intersection structure. We're really making use of that here. Now, the idea is if you have a code word from this set where m is at most q squared minus 1, let me just make sure I can write that. Yeah, so where m is at most q squared minus 1, you can check that, in fact, that polynomial has total degree at most q minus 1. And so you can interpolate the value of f from the q points Yeah, so the polynomial in x and y has total degree at most q minus 1. So when you limit it to a line, you're going to get a univariate polynomial of degree at most q minus 1, which can then be interpolated from the value on f on the other q points of that line intersected with the Hermitian curve. So it's lovely, right? And it's just using the same idea, only restricting to points on the curve. But we, in fact, have that the rate here is, again, pretty bad. And as our codes get really long and we go over bigger fields, our rate goes to 0. So with a wonderful group of collaborators, including Hiram Lopez, Gretchen Matthews, Fernando Pinheiro Gonzalez, and Mary Wooters, we decided to try and apply this idea of lifting to the Hermitian curve codes. So how does that work? The idea is, well, let's start by taking polynomials in 2 variables and thinking about how those can restrict along lines to polynomials of 1 variable. So we say that a polynomial of 2 variables agrees with a polynomial of 1 variable on the Hermitian curve if when you plug if you take the function of the line along the, sorry, how do I say this? So if h of t is the line parameterization and f is the 2 variable function, the idea is that if the values of that 2 variable function at all points along the line, at points along the line are equal to some 1 variable function for every point that is actually on the Hermitian curve, for every h of t that is actually an element of the Hermitian curve, then we say those 2 functions agree on the Hermitian curve. So if L is the set of all these non-horizontal lines that we were interested in, non-tangent lines that we were interested in, we're going to define our set of functions to be, for our evaluation code, to be the set of all 2-variate functions. So that for each line in this set of lines that we care about, the function on the line agrees with some polynomial of degree less than or equal to q minus 1 on the Hermitian curve. So it's not too hard to check that this is in fact going to be a linear space. And the Hermitian lifted code is just going to be the evaluation code we get by evaluating all of these points on the Hermitian curve. Okay, so now the observations that we have here is that on each line is q plus 1 points. And so we know that when we limit to those values, to those q plus 1 points, we're going to get a polynomial of degree at most q, just because we only have q plus 1 values. But now a function that has degree at most q minus 1 actually has unexpectedly low degree. So again, we can use the same recovery method that we used before, just because that is designed, we specifically designed the code that way. And so we're going to end up with a code with availability q squared minus 1 and locality q. The minimum distance of the code we can bound through using geometry as given here. And in fact, what we proved, which is pretty exciting, is that in fact, the rate of the code is bounded below by a constant. Now, this constant seems awfully small, but in fact, it's not 0. So that's actually a pretty big deal because we saw before that the rate goes to 0. Okay, so just to give you a little bit of interesting work that's happened since then, with an undergraduate student, I recently was lucky enough to be able to extend our methods from the previous to odd primes and get a bound that also doesn't look that great, but is also not 0 for any odd prime p. But some really nice work that was led by Fernando Pinheiro Gonzalez with several RU students, was actually able to improve on what my student Nama Neveau and I did, and was able to come up with a quite nice bound for all primes. Okay, so what we see here is that our rate is really bounded below by 1/4 times p plus 1, which is very nice. There was some further work in this area by Gretchen Matthews with her student Aidan Murphy and Travis Morrison, who actually have explored the parameters for other lifted codes. Okay, so I realize now that I have more things to say than I have time. So let me just give you a quick once over on this next idea, and then we'll skip over the technicalities of it. Okay, so the big idea was polynomial interpolation. What I'd like to point out is that you can actually use this idea in many settings. So a big idea that's due to Barg, Tomo, and Vladu was that we could define locally recoverable codes on curves using this notion of polynomial interpolation through the following idea. So let's say you have a curve and then you have a map to another curve. So G is just, a map here. So for example, if you have the curve y x cubed equals some function of y, and then your map is just projection down onto the y coordinate, that would be a map from your curve to the projective line in y. Okay, so now the idea is we're going to create an evaluation code on x that is locally recoverable by using the following clever idea. We're going to choose points on x that when we map them down to y, pull back to full fibers. In this case, they would be fibers with degree 3 or with 3 points because it's the degree 3 map. So what we're going to basically do is throw out any ramified points or small fibers that are defined over a larger field. And we're going to choose our evaluation set to be all of those points on x that are in these full fibers above points on y. And so the big idea here is that we can define an evaluation code where the functions are polynomials in 2 variables, in this case, x and y, in our picture here. And then the idea is that we can, when we look on fibers above a fixed point on the bottom curve, the function on the large curve restricts to a very simple function, and it allows us to use those fibers as recovery sets for our code. So the reason this works is the following. So let's say that f of q1 is erased. Then the recovery set that I've described would be the other 2 points in the fiber with q1, that is q2 and q3. The idea is that, in fact, q1 and q2 and q3 all have the same y value because they're in the same fiber in this projection map. And so when we restrict to that fiber, this function of 2 variables really just becomes a function of 1 variable. Now, my linear space of functions here was just linear in x and quadratic in y, but now that we've limited to y, it becomes just a linear function in x, which has the form ax plus b. And so the idea is that since this is just a linear function, we can find a and b by looking at f of q1 and f of q2. And so we're able to interpolate this linear function and find the value of f on q1. Okay, so this idea is really clever, and I think what the exciting thing that that my group with Gretchen Matthews and Katie Haymaker brought to it was the idea to try and really extend this idea to get more recovery sets from curves. And not to go too deeply into this, basically the idea was to create a curve that had maps to many lower curves. And a really great way to do this is through fiber products, okay? So this is a quick depiction of a fiber product here on the bottom left, and you can kind of see it in a cart as a bunch of maps on the right. So again, I won't go into this too much since I am short of time, but the cool idea here is that you're able to use this to construct codes with as many recovery sets as you want, thereby getting high availability from the geometry of this fiber product construction. Okay, so I'm going to skip this example. It's very, very fun, but I'll just go past it. I did want to draw attention to some really nice work with Maria Chara, Sam Kotler, Bianca Thompson, and Mackenzie West, where we were actually able to find the minimum distance of these codes. So if you're excited about this kind of work, definitely reach out to me or to one of these great collaborators. Okay, so I'll just end by speaking just a little bit about hierarchy, since I told you about that. Reed-Muller codes with m greater than or equal to 3 have natural hierarchy and availability. You can think of the plane, the space here. So for here, I've depicted a 3-dimensional space as the evaluation set. And you could think of planes within that as being the evaluation points for the middle codes. And then lines give those lower codes where you have local recovery. And you can also kind of use higher dimensional linear spaces and translations in this idea. So this is easily extended for many levels of hierarchy. If you had m equals 10, you could have 10 levels of hierarchy here. This is very flexible in lots of ways to recover, but again, it has kind of a low rate. So lifting, the idea we brought up before, could help. This hasn't actually been explored, but it's something that I'm very excited about. So in those fiber product codes I described, you have natural hierarchy there as well. For your lower code evaluation set, you could have points where all coordinates but one are constant. And in the middle code, the idea is that you can have a set of points where some smaller collection of coordinates are constant. So some recent work with Haymaker and Matthews is to understand the hierarchical parameters of these, which you don't need to worry about too much because I know I didn't introduce like what these symbols are, but I'd be happy to talk about that more offline. Final frontier here is going to be what other geometric constructions we can use. So why not extend this idea of Reed-Muller codes to surfaces? And so we've recently been exploring Art and Schreier type surfaces, where the code would be on the surface, but then you find middle codes by restricting to the intersection with planes, where you would get Art and Schreier curves. And then your lowest recovery sets would be fibers inside those curves. So for example, mapping down, as we saw in the picture earlier, to the y coordinate and pulling back. Okay, so that's really the story I want to tell you. The big takeaway is that geometric constructions offer a natural and flexible way to create locally recoverable codes with many recovery sets and hierarchy. So I think the frontiers are really all over the place. This is kind of an open area with lots of exciting work happening, but lots of good questions to answer. So I'd really like to understand what's going on with surfaces. And can we come up with a way to capture these ideas of hierarchy and availability, which are sort of opposite, right? Disjoint versus. And are there ways that we can kind of look at realms in between there, where we have recovery sets with varying levels of overlap? Okay, thank you so much for your time and attention. I'm very happy to take any questions that you have.
Thank you very much, Beth, for a very nice lecture, a very clear introduction and explanations. I was wondering if anybody in the audience has any questions or comments for our speaker. This is a good time to speak your mind. Any questions or comments for our speaker?
Well, I have a general question.
Yes.
If a student wants to learn these topics, what bibliography do you recommend?
That's a great question. So I think for codes, there are a number of great books about coding theory out there. But to learn about algebraic geometry codes, I think that the reference that I've always used is Codes and Curves by Judy Walker. It's available for free as a PDF. I'm going to just write it in the chat right now. So Judy Walker is a professor at the University of Nebraska-Lincoln who has done a lot of great work here. And this was constructed as an undergraduate reference for a summer school that she taught about these topics. So that's a great reference to learn about algebraic geometry codes without too much background required. Yeah, okay, so I see there's a question in the chat that asks why determining the exact minimum distance of linear encodes is a hard problem. That's a great question. So in the case of Reed-Solomon codes, you could see that there was some underlying algebraic geometric structure that made it really easy to reason about the number of zeros that was possible for a code word. We could just think about how many zeros are possible for a polynomial. In non-geometric constructions, there's not that structure to lean on. And the best way that we have to determine the minimum distance of a code is really to just run over all of the code words and look for the weight of minimum, or to look for the word of minimum weight. And so, as you can imagine, that's a very time-consuming process. It's exponential in the dimension of the code because you have to look at q to the k code words. And so if you don't have any geometric structure to lean on, that it's like the simplest general algorithm that's known is just the brute force one that you couldn't that you really wouldn't want to do. So for example, there's coding theory packages in Sage and Magma, and if you ask them to find the minimum distance of the code, they're essentially just running over all the code words. And so even in these implemented packages, you'll find that as soon as your dimension gets like beyond 10, or maybe not even up to 10, it becomes really, really very difficult in order to find these this minimum distance. So I don't know if that gets at the exact reason why it's hard. It's just that nobody knows any good way to do it beyond just this brute force search. Yeah, thanks. That's a really good question. And it's somehow hard to accept that it should be so hard.
Any other question or comment? Well, we have 5 minutes until the next speaker, so maybe this could be a good opportunity to take a break. But before we do, let's thank our speaker once again.
Thank you very much for the invitation to be here and for the time and attention of those of you in the audience. This is a really wonderful event. And yes, thank you again for letting me be here.
Thank you. Thank you again for a nice talk, and see you all in 5 minutes.
Thank you so much.
Welcome back to the for the second speaker this morning. I am delighted to introduce a good friend, Mauricio Medina Bárcenas. Mauricio is currently with the Centro de Ingeniería y Desarrollo Industrial in Santiago de Querétaro, and he is going to tell us about some lattices in the study of modules.
Thank you, Sergio. Thank you, the organizer, for this invitation. I want to try to talk about, it's a research that my colleagues and I were doing in the past years. My colleagues, Lorena Morales Callejas, Lisbeth Sandoval Miranda, and Ángel Saldívar Corichi. So this research is about try to study the models and rings using lattices, some kind of lattices. All these ideas come from, it could be, think of a point-free approach in some way. So let's start with the definition of a lattice. So, a lattice is a poset, a partial order set, in which every pair of elements have a supremum and an infimum. That's a lattice. We want complete lattices, that is, not just a pair of elements, but any subset has a supremum and an infimum. Here is the notation for those supremum and infimum of a subset. And in particular, in this kind of lattices, we have a lowest element denoted by 0 and a greatest element denoted by 1. So here we're going to start with many definitions. So if something is not clear or you want to say, if you want to see the definition again, let me know. So our base is a complete lattice. Now, we're going to give more properties to this complete lattice in order to get more properties and adequate it to our examples. So a complete lattice is an idiom if the following conditions are satisfied. The first one is the modularity. It's a kind of distributivity, but we need that some of the elements is below the other one. This property of modularity comes from the lattice of modules. And also we need upper continuity. So the infimum distributes arbitrary supremums, but not for any subset. We need directed subsets. That is, a subset is directed if for any pair of elements in this subset X, there is a third element above them. So this is an idiom, modularity and upper continuity. Another complete lattice that appears in many mathematical contexts is the concept of frame. So a frame is a complete lattice in which we have the distributivity for any subset. So the idiom upper continuity is just for directed subsets. Frame is distributivity for any subset. And then when we when we are trying to adequate lattices to algebraic structures, some other operations, some other properties are needed. So we have here another kind of lattice. It's called quantal. So a quantal is a complete lattice with an extra operation, an associative product, which is distributive with respect to suprema in the lattice for both sides. Because in this case, the product might not be commutative, so we need the distributive for both sides. Okay. Okay, so idiom, we have very weak distributivities with the infimum and the supremum. A frame is a distributivity with all the subsets. And a quantal is a lattice with a product, with a multiplication, if you want to think that in that way. Then, with my colleagues, we define a quasi-quantal. So a quasi-quantal is a complete lattice with an associative product such that this product is distributive, but only for directed subsets. So we didn't have all the distributivity like in quantal. We wanted a weaker condition. So we defined quasi-quantals in this way. So which are the implications? Every frame is an idiom because the distributivity is total in the frame. In the other way, a frame is a quantal where the product is given by the infimum. Okay, but in general, we don't have a comparison between quantal and idiom. But quasi-quantals make the class of quasi-quantals englobes or all the previous lattices can be seen as a quasi-quantal. The quantal with the product that it has, and an idiom is a quasi-quantal with the infimum. So quasi-quantals gives a better framework for working with this kind of lattices. So, okay, something in the chat. Complete lattices, lattice where every subset possible infinity there exists a suprema and infima lattice, for example, a lattice of.
Don't worry, Mauricio. People were asking questions, but Lisbeth answered, so you're okay. Don't just ignore the chat.
Okay. Thank you. And so these are the lattices we are working on. Actually, most of the results are given in for quasi-quantals. That is the more general concept. So some examples. This is a tiny lattice, which is not any of the previous one. So this lattice is complete, but it doesn't satisfy modularity. So it's not an idiom, It's not a frame, it's not a quasi-quantal, it's not a quantum. The pentagon lattice. The canonical example for frames is the topology of a space or a topological space. So this is where point-free topology emerged in some way. So given a topological space with topology OS, the topology is a complete lattice where the suprema are given by unions. The infimum is the intersection of the open sets and take the interior. The greatest element is the space, and the lowest element is the empty set. So this complete lattice is a frame because the supremum is given by the union, and when you intersect that that union with another open set, the distributivity of sets gives the distributivity law in the definition of frame. So this is the canonical example, the canonical, not trivial example of a frame, because maybe the easiest example for a frame is the power set of a set. But we can say that the less trivial example of a frame is a topology. So, R models. Given an R model with R and an associative ring, not necessarily commutative, with unit, we can take the set of subset or submodels of this module M, and this is a complete lattice. The supremum is the sum of submodels. The intersection is the infimum is the intersection of the submodels. The greatest element is the module itself, and the lowest element is the zero submodel. So this is our canonical example of idiom. It satisfies the modularity, and it is upper continuous. In general, these lattices are not frames, neither quantals. So if you want to have in mind a frame, you can think of the topology of a space. If you want to have in mind an idiom, you can think in the lattice of submodels of a model. But we also have the ring. So for any ring, by the last example, we have the lattice of left ideals of the ring. So this is a complete lattice, it's an idiom, in fact. But the ring has a product. With this product, and given two left ideals, we can construct another ideal, the product of these I and J ideals. So this product is given by the finite sums of products, one element in I and one in J. So this gives us a quantum. So topological space gives frames, models gives idioms, rings gives quantals. So the concept of quasi-quantal is a little more complicated, but we have an example. For this example, we need to introduce the notion of preradical. So preradical is a subfunctor of the identity functor. That is, for any module, this preradical gives a submodule and is well behaved with the restriction. The class of all preradicals on R mod is denoted by RPR, and this class can be ordered. So one preradical is less than another preradical S if and only if Rm is a submodule of Sm for every module M. The term big here is because it's a class, so it's a big poset. There is a supremum for any family of preradicals. It's the preradical which in each submodule is given by the sum of the submodules given by the images of Re. But rings aren't a particular case of models. Yes, they are. Yes, the lattice, I am reading the chat. Jose Armando is asking about the rings and models. Yes, every ring is a model. So the left ideals form a complete lattice, which is an idiom. But we have an extra operation, which is the product. And with that product, the lattice becomes a quanta. So in particular, it's an idiom, but it becomes a quanta. I hope I answered your question. So also for any family of radicals, there is an infimum, and it's given by the intersection of the images of the submodels given by the radicals.
Mauricio, you can
Yes,
close your chat.
I can close it.
We can see your chat.
Yes, I can close it.
Okay.
I stop.
Yeah. Okay. Thank you.
Radicals, supremum is the sum, infimum intersection. The identity functor is the greatest radical, and the zero functor is the lowest radical. So we have a big lattice. This lattice has a product, and is given by the composition of radicals, the composition of functors. And there are some kind of radicals which satisfies this property. To compute the image of the radical in a submodule, you only have to know the image of the whole module. So these radicals are called left exact. This, the set, in this case, it is a set. So there are so many left exact radicals. The set are left exact radicals. It's a big lattice, it's a lattice, but we have to change the supremum. So we have this supremum for any family of radicals, but if we put some restrictions in the radical, like this one, to be left exact, it could happen that when we take the supremum, that per radical is not left exact, so we have to close it. But here is the thing. If this supremum is taken over directed sets, we don't have to change it. So R left, this set of left exact per radicals, have the same supremums over directed sets. And this makes R left a quasi-quantal with the product of composition. In general, the composition of per-radicals is not distributive over supremum. But here, for directed sets, it is. So this is an example of a quasi-quantal that may not be a quantal and is a little more technical. So we have the lattices that we are working on. Quasi-quantals is the general one, but inside of the class of quasi-quantals, we have quantals, we have idioms, and we have frames. So how
Oye,
those,
Unicen, no me vengo aquí. Iba a ir, marica, me meto ahí donde venden los pizza.
how do we
pizza,
study these
se llama
lattices? Well,
los panes esos para una pizza.
someone is with the microphone on. This complete a way to study lattices is using some kind of functions called nuclei. So a nucleus on a complete lattice is a monotonous function from A to A, such that the image is above the element. It commutes with infimum. It's idempotent. And we are interested in the fixed points of these kind of functions. So this is when we want to study a lattice, a complete lattice. A good way to do it is to look at the nucleus, the nuclei on A. And then to look at the fixed points of that nucleus. Okay. If we are working with a quasi-quantal, since the quasi-quantal has a product, we are working with nuclei, which change the multiplication by the infimum. This is a multiplicative nucleus. So the nucleus in a product is the infimum of those elements. So if we have a quasi-quantal A and a nucleus on A, V, if this nucleus is multiplicative, then the fixed point set is an idiom. And then if in our quasi-quantal there is an absolute distributivity for any side, we only need one. In that case, the set of fixed points is a frame. So we are interested in the properties of the fixed points. So in the first case, we only have an idiom. In the second case, with an additional hypothesis, we have a frame. We need an extra condition when we are talking about all this gonna make sense with the examples that come later. So we need an extra condition, which is called start. A subquasiquantal is just a sublattice where the product is closed, which B is closed under the product. So the condition start is that the lowest and the greatest elements are in the elements of B, and every time that we multiply by the greatest element, that product is below of the element. So here, in the definition of quantal and quasiquantal, it's only said that there is a product. It's not said if there is a unit for that product. In general, might not, or yes or no, we don't know, but we want this condition. When we multiply by the greatest element, the product is below the element for any B in the quasiquantal B. Oh, this is all this work started with try to give a more general definition of a prime element. So the definition of prime element that we gave was the following. We have a quasiquantal and we fixed a subquasiquantal. So an element in A, in the big one, it's a prime element. It's a prime element relative to the quasiquantal B if always that the product AB is below P, where A and B are taken in the quasiquantal B, then A is below P or B is below P. So this is a little more general definition of prime element. We can say that the common definition of prime element is when we take A equal to B. So this is a little more general definition. And if we have prime elements, we have a spectrum. And if we have an spectrum, we want a topology. So we have a quasiquantal A, a subquasiquantal B, and the condition star. We have the spectrum relative to B. And this spectrum is a topological space with the open sets, with the Zariski open sets, basically. We need the condition star in order to get a topology. Without the condition star, it's possible that we don't get a topology for this space. So, for any element B, we have the UB, que es an open set. So this defines a surjective supremum morphism, which has an adjoint, which goes in the open direction, which is defined by the rule. So we have the topological space, we have the assignation of open sets, U, we have a morphism in the opposite direction, so we can compose them. So the composition gives a nucleus on B. So which are the properties of this nucleus? For any B and B, mu B is the greatest element of B, which is below the infimum of all primes containing P. It's not an equality. It's just the greatest element of P below that element, below that infimum. It's a multiplicative nucleus. It changes the product by infimum. The fixed points, the set of fixed points of this nucleus is isomorphic to the topology, but as idioms, just. If we add the condition of an absolute distributivity in either side, one of them, then we have a frame, and that frame is isomorphic as frames to the topology of that space. Okay, we'll start with the applications to models and frames. So, what was the idea? The idea was to define some primes elements. With those primes, we define a spectrum, a topological space, in the Zariski's way. We get a nucleus, and that nucleus has these four properties. So now we are going to translate these results to rings and models, most for models. So let's fix a model. So the lattice of submodels is an idiom. It's possible to define a product of submodels. Like in the ring, we have a product of ideals. It's possible to define a product of submodels. And one definition of this product is this one. It's a kind of trace. This product, in general, satisfies an absolute distributivity. So here his work, this work started. This was our example of quasi-quantal and all these ideas. Absolute distributivity in general. But this product might not be associative or distributive for the other side. So we have to add an extra hypothesis on the model M, kind of a projectivity condition, in order to get that the lattice of submodels of a model M is a quanta. So this product with the hypothesis P is associative and is distributive over supremos, over the sum of submodels. A submodel is fully invariant if Fn is contained in an N for every endomorphism of M. We can consider the set of full invariant submodels of M. So with the condition P, the lattice of fully invariant submodels is a subquantal of the lattice of submodels of M. And this subquantal satisfies the condition star. So the condition star came from the lattice of fully invariant submodels. That's where we got that. If we have a product, we can define semi-prime submodels whenever the product of the same element is below, in this case, the product of L with L is below N, then L is below N. This is a semi-prime submodel. So what can we do with this? Okay. We have a quantal, we have a sub-quantal with the condition star. We can form, we can form the relative spectrum. In this case, in the last, in the other slides, this is A, and this is B, and this is the relative spectrum of A to B, because we denote it in that way. So this is a topological space. There is a multiplicative nucleus on the fully invariant submodels, and the set of fixed points is a frame, and that frame is isomorphic to the topology of this space. And which are the submodels fixed by mu, by the nucleus mu? Well, a submodel is fixed by this nucleus if and only if is the total M or is a semi-prime submodels. So the semi-prime fixed points mu, this set of semi-prime submodels is isomorphic to the topology, is a frame isomorphic to the topology of this space. Maybe someone is looking at this and it seems quite familiar. In the case of a commutative ring, this analysis is the radical ideals. In a commutative ring, the semi-prime ideals are the radical ideals. And this is saying that the radical ideals, well, the nucleus mu is take the radical, and the point number 2 is saying that the radical ideals in a commutative ring is a frame and is isomorphic to the Zariski topology of the spectrum of the ring. Oh, this definition. A frame is spatial. It is isomorphic to a topology for some topological space. And if every quotient of this frame is spatial, it is said that A is totally spatial. So why I am giving this definition? Because we have this proposition. For a model with the property P, and with the hypothesis that the every factor model has finite uniform dimension, this frame, which is spatial, returns to be totally spatial with the condition of finite uniform dimension. So in commutative algebra, we have the spectrum of a ring, but we have also the maximum spectrum. So we can do the same for the maximum maximal elements in a quantal. So if we have a quantal and a sub-quasi-quantal satisfying star, and we need this for the elements in. If we have a maximal element, then that maximal element is a prime. So it's the same as in commutative algebra. Every maximal ideal is prime. So here, is the condition that when a maximal element in a quantal is maximal. So maximal, the set of maximal elements of the quantal A is a subset in this relative spectrum. And we can give the topology of subspace. So this MB are the open sets in max A. And we have again an adjoint which gives us a nucleus, a multiplicative nucleus. And this multiplicative nucleus is the greatest element of B contained in the intersection of all maximal elements containing B. The set of fixed points is a frame which is isomorphic to the topology of the maximum spectrum. So what happened in models? A full invariant submodule is primitive if there exists a simple module such that P is the intersection of all nucleus of morphisms from M to S. In rings or in combinatorics algebra, primitive submodules, primitive ideals are the annihilator of a simple model. So this is the generalization of that. A submodule is semi-primitive if it's an intersection of primitive submodules. So in the case of modules, we have that the maximal submodules are contained in our relative spectrum, and therefore the maximum spectrum is a topological space. There is a multiplicative nucleus such that the set of fixed points is a frame which is isomorphic to the topology of this maximum spectrum. And the submodules, which are fixed by this tau, are M or the semi-primitive submodules. In rings, when you in the zero submodule, you get the Jacobson radical. So what we have as a consequence, a module M is co-semisimple if every submodule is an intersection of maximal submodules. Co-semisimple modules are a generalization of B rings, Villa-Major rings. Or in the commutative case, these are a generalization of von Neumann regular rings. If we have a co-semisimple module which satisfies the condition P, the lattice of fully invariant submodules is a frame. This proposition in commutative algebra is if we have a von Neumann regular ring, the lattice of ideals is a frame. Okay. So we just defined in some way two topological spaces. One was given by some primes elements, and the other one was given by maximal elements. So we wanted to study some topological notions in these spectrums. One topological notion that we chose to study was the normal. So this condition of normality comes from topology, it's inspired in a normal topological space. So as a quasi-quantum is normal, if for every two elements which the supremum is the total, there exists another two elements which these conditions in some way is the normality in a topological space. So these two lemmas are, if we have a quasi-quantum with maximal elements and a nucleus, a multiplicative nucleus, when the set of fixed points is normal, so the condition is that the nucleus fixes each coatom. If the nucleus fixes each coatom, then the set of fixed points is normal. And in the other way, if the nucleus fixes the lowest element and the set of fixed points is normal, we can recover that the quasi-quantum is normal. What happened with the topological spaces that we define? Well, with all our conditions, condition Sartan and multiplicative nucleus, the relative spectrum is a normal topological space if and only if the fixed point of the nucleus mu is normal. So in the case of modules, the relative spectrum is a normal topological space if the frame of semi-prime submodules is normal with the definition we gave. And the same for the maximum. The maximal spectrum is normal as topological space if and only if the frame of semi-primitive submodules is normal with the definition we gave. And that's all. These are the references. These are general references for the study of lattices and point-free topology. These are some of our papers where we do all this analysis. A reference for radicals and a reference for quantals. And that's it. Thank you very much.
Thank you very much, Mauricio, for a nice talk. Does anybody in the audience have questions or comments for our speaker?
Hello, Mauricio. Are you hear me?
Yes.
Yes. Well, thank you so much for this nice talk, and thank you for talking about our work in progress. And I just have a question. This is for my students. So if a student wants to learn these topics and to learn more about this research, what do you think this will be the way to start? I mean, what could be the first bibliography that you recommend, or what courses you think they should take for a student?
First of all, First of all, I think that this book by Calugariano, it's a good point to start, because in this book you can see how many properties of models and rings can be seen in the lattices. So sometimes concepts in models are concepts in the lattices, and it's not needed the algebraic conditions. So this book can be a good start to be familiar with the notions of lattices in algebraic situations in model theory. And later, maybe some sections in the book of Johnston, because we are working with nuclei. So these operators in lattices are presented in this book of Johnston. And I think later he or she can read our papers. I think we gave very good introductions and preliminaries in those papers.
Any other questions or comments for our speaker?
So thank you, Mauricio.
Thank you.
Let us thank our speaker once again. And I am not really sure how long the break is now. When do we reconvene? We cannot.
Microphone is off. Okay.
Okay, thank you so much for this talk, Mauricio. It was
Thank you for the
interesting.
invitation.
And we have some minutes. And I want to say thanks, Professor Sergio Lopez, for be part of the scientific committee and for your support to give the presentation of the first two talks. So
Thank
I
you. It was my pleasure.
wait 2 minutes now.
Bye-bye.
Thank you so much.
Thank you, Sergio. Nice to see you.
Hello, everyone. It's my turn to introduce to the next speaker. And it's a pleasure for me to introduce to Dr. Johannes Rau. And first, let me say thank you very much, Professor Johannes, for accepting the invitation to give the talk and participate in this conference. Professor Johannes works in the Department of Mathematics at the Universidad de los Andes in Bogotá, Colombia. Dr. Johannes actively participates in different projects to give more visibility to mathematics. For instance, the Latin American online seminar on real and tropical algebraic geometry. His research area is tropical geometry and his connection with enumerative geometry, real algebraic geometry, and intersection theory. On this occasion, Dr. Johannes, we will talk about patchwork of real algebraic varieties in Hilbert dimension.
Yes, okay. Thank you very much for the invitation. Yeah, it's a great pleasure being here. Yeah, so in this talk, okay, I'm sorry for changing the title a little bit, but the title I announced is also correct. So we're going to talk about tropical geometry, and we're going to talk about its applications in real algebraic geometry. So just maybe to a quick announcement that this talk will be there will be no number theory. There will be a little bit of algebra, but not very much. There will be some combinatorics, and there will be some geometry. So I hope that I'm not. Well, I hope it will not be too far away from what people are interested in, but we'll see. So the plan is first a quick introduction to tropical geometry, and then there's and then I will talk a bit about these applications in real algebraic geometry, some older ones. This is what is called verbose patchworking, and then in the last part I will talk about some more recent work where we try to apply these tropical techniques. So let's get started. Let's get started with a little bit of algebra that is contained in my talk. So one way of starting with tropical geometry is actually just as in the classical case in algebraic geometry, just that we have to change a bit our base field, and we actually have to change it to not even a field, but to what we call the tropical numbers. So the tropical numbers are just the real numbers together with an extra element minus infinity. And we just define operations on tropical numbers in a strange way, but I will explain in a second where this comes from. So we define the sum of two numbers in the tropical world as the maximum of the two numbers. And we define the product of two numbers in the tropical world as just the ordinary sum of two numbers. And well, with this definition, we can already talk about tropical polynomials. So tropical polynomials are just ordinary polynomials. So here my example is in two variables, x and y. And they're just ordinary polynomials with coefficients in tropical numbers, just that now all the operations, so the products here and the summation here, that you should think of them as being, so we're using here these tropical operations. So if you translate what this actually means, well, so for example, a monomial like this, well, it just corresponds to an affine function. The exponents turn into coefficients because x to the I, that's the, that's x times x, but tropically x times x, etc. That means summation. So it's just I times x, and then we're summing those, and the coefficient is actually just the constant of this affine function. And then the summation, of course, just turns into taking a maximum. So what I'm saying here is that the tropical polynomial is just maximum of a collection of affine functions. And here is the simplest example possibly. So that's the tropical polynomial 0, x, and y. And well, if you just translate what this means, it just means take the maximum of 0, x, and y. And well, that's the graph of this piecewise linear complex function. And so now we would like to do usual ordinary algebraic geometry over these over tropical numbers. It means we would like to talk about the zero sets of tropical polynomials. Now, be careful a bit. So 0 tropically is the element minus infinity, right? Because we defined addition to be the maximum. And well, the neutral element with respect to maximum is this element minus infinity that we added. So in particular, this 0 here is not is the kind of it's the usual number 0, which is not the neutral element with respect to tropical addition. So in particular, we see that this polynomial, of course, since it's a maximum, it actually never attains the value minus infinity. It's impossible. So we have to define the zeros of this polynomial in a kind of different way. And the definition, which turns out to be the correct one, is the following one. So we define the tropical hypersurface associated to a tropical polynomial as the corner locus of the function f. So let me explain what this means in the example that we just saw. So we saw that this function is piecewise linear. It has these 3 domains of linearity, and then it has these three rays where the function breaks. And this is exactly the locus that we call the zero set of this polynomial. Okay, so if I draw this just in the plane in R2, then well, I have these 3 domains of linearity. Here the function is y, here the function is x, here the function is 0, and it meets along these 3 rays where the function actually breaks. And so what we call the hypersurface associated to this polynomial is just a collection of these 3 rays here. Okay, and since this is a polynomial of degree 1, I'm going to call this the tropical line. And let me show you one more example. So this is a tropical conic. So here I'm doing exactly the same thing, but now my polynomial is of degree 2. And well, here, so this is the graph of the polynomial. It's a convex function which is piecewise affine, but it has these parts where it breaks. If you draw it in the plane, you get these 6 domains of linearity, and you get this graph which kind of separates the different domains of linearity, and that's the tropical conic associated to this polynomial. Just to show you a few pictures, so I have many pictures in my slides. I hope this is not too informal, but here just to show you a few more pictures. This is a quadric surface in R3. So here I'm using a polynomial in 3 variables, but of degree 2. And I think I have one more picture. Yeah, this is a picture of surface also in 3 variables in R3, but now of degree 4. So this is a quartic surface. So we see that in general, what these kind of strange definitions, so far I haven't given any motivation, but these strange definitions, what we get from them is some kind of polyhedral complexes with some very particular properties. So for example, in these curve examples, we saw that they have some kind of some special directions. We always have this direction to the left, to the bottom, and in the diagonal direction, etc. And well, they are some kind of polyhedral objects that one might study. But of course, the question is why and where do these definitions come from? So in this talk, the idea that I want to give you about these pictures is that they are really images of classical algebraic varieties in logarithmic coordinates. Okay, so let's stick to the case of curves in the plane. So basically, I'm having right then I have two variables. So I have the variable z and the variable w. let's think of them as complex variables. So I'm looking at complex curves in the plane, and now the logarithm or the tropical coordinates associated to these coordinates are just you take the absolute value of the complex number and you take the logarithm of the absolute value. And so x and y would be the corresponding tropical coordinates. And well, this already partially explains my strange definition of tropical arithmetics, of tropical operations, since of course we know that the logarithm turns a product into a sum, right? And so that's exactly why I define the tropical product as the usual sum. And what about the sum? Well, here it's not quite as easy, so there's no general rule, but actually that's why I put here a t in all of these formulas. But I actually want to be allowed to change the base of logarithm that I'm using. Okay, I want to use different bases of logarithm here, because actually what happens if you, for example, use a very large base of your logarithm? So what does that mean? If you sum two numbers, and let's say this number has logarithm 1 and this here has logarithm 0. Well, if your base is very large, it means that this first number is very large compared to the second number. And it means that in this sum, essentially only the first one will matter. So kind of on an asymptotic level or in the limit, you can say that really only the larger number matters in the sum, and that's why we define the tropical sum as the maximum of the two logarithms. Okay, so this of course is just the vague idea that okay, we want to use logarithmic coordinates in algebraic geometry, and this leads us to tropical arithmetics, but it actually has a very concrete practical consequence. So I want to really tell you how to tropicalize an algebraic variety, or rather a family of algebraic varieties. So here you see x is a subset of c star to the n times the positive interval. So this is my parameter interval, and I have here a family of algebraic varieties. I take c star to the n because I want to exclude the coordinates to be 0, because otherwise I cannot take logarithm. That's kind of just, there are ways to compactify this, but for simplicity, let's just look at c star to the n. And I use the same map that I used before for each of the coordinates. So I have a map log t from c star to the n to Rn. For each coordinate, I take the absolute value and I take the logarithm with respect to the base t. And if you do that, so now kind of by definition, we say, so okay, what we're doing now is we take an element in this family. So we take an algebraic variety associated to the parameter t. We take its image under this logarithm map. And what you get so far are actually quite strange pictures. So here is an example of a line. And if you just take this logarithmic picture of the line, what you're going to get is this picture here. It's called an amoeba. But what we're really interested in is now taking a limit. So now we're going to increase the base t. We let the base go to infinity. And this actually has the following effect. So now my amoeba is going to start to shrink. It's going to start to starve, kind of. And in the limit, I'm going to end up with kind of a skeleton of this amoeba. And I'm going to actually end up with a tropical curve. So in this case, it's just going to be the tropical line. Okay. So this is a very simple example. Since, in fact, here my family is a constant family, you see that this equation doesn't depend on the parameter t. So it's a constant family. And in this case, I'm just ending up with a tropical line. Here is a bit more complicated example. So here I'm having a cubic equation in two variables. Okay, so now it depends on this parameter t now. For each value of t, so say t is equal to 5, then I just have a cubic equation here, and I have a cubic curve associated to this polynomial. And now if I take this logarithmic picture of such a cubic curve, I'm gonna get something like this. So again, this is called an amoeba. Now it already looks kind of a bit more interesting. It has several tentacles going off to infinity. It has this kind of this empty hole in the middle. But again, what happens if you increase the base t is that this amoeba is going to starve, and in the limit you're going to actually end up with a tropical curve. Okay, and I can't even tell you exactly which tropical curve. So there's no kind of to connect with the previous with the introduction. Let me tell you how to compute the limit in this case. So what I did is just I took this polynomial here, which depends on the parameter t, and I tropicalized it. So tropicalizing it means I construct a tropical polynomial which has exactly the same terms, but the coefficients of this tropical polynomial are just the exponents of the function that I see upstairs, the coefficient function that depends on t. Okay, so for example, here the coefficient upstairs is t to the -1. That's why tropically my coefficient is going to be -2. Here I have t to the 1, which is why tropically I have coefficient 1. Here actually I should say I have t to the 0, no dependence on t. This is why here the coefficient, the tropical coefficient is 0, the real number 0, okay? And one more, so here I have the coefficient -1 because upstairs I have t to the -1. And what you see here, so this limit that you get in this case for this particular family of cubic curves is exactly the curve, the tropical curve associated to this tropical polynomial. Okay, so this is another example. So this tropical polynomial here, if you draw this convex function and you look at the corner locus, you're going to get exactly this picture here. Okay, so this, I hope, in some sense, explains a little bit why did we do these strange definitions in the beginning, and what's the purpose of studying these objects. So really, one should think of them as like images of algebraic varieties in logarithmic coordinates. Okay, I think I have just one more picture here of a line again, but this is a line in 3-dimensional space. So here, this kind of the surface that you see is the amoeba in this case. And again, if you increase the base here, then this amoeba shrinks, and in this case, it would shrink again towards this red skeleton that you can see in the middle. So maybe that's already other questions until now.
I think no.
Okay, let's keep going. So this was my very quick introduction to tropical objects and where they come from. Now I want to tell you about how to use them. So now I'm gonna do a small jump. We're gonna talk about Virus patchworking and kind of the context in which this patchworking arises. So a bit of a different angle now. The very general problem here is the study of the topology of real algebraic varieties. So varieties defined over the reals, and then we want to also look at the real solutions of these equations, and we want to study the topology of these spaces that come up. Okay, so the very simplest instance would be the following. You give me a real polynomial in 2 variables, and you draw just all the real solutions of this polynomial. And the question is, what are the possible shapes of this solution set? Okay, so this is a very basic question. I'm only asking about the topology of this solution set. So I'm not interested in more advanced properties like curvature, etc. I really only want to know how many components has this solution set and how can these components be arranged in the real plane. Okay. I guess you can imagine that this is kind of a very old and a very natural question. It often goes under the name of Hilbert's 16th problem, because Hilbert, in his famous list, included a problem exactly of this type. And yeah, in the last century, let's say there was quite some efforts were made to just study, to just give basically topological classification of real algebraic varieties. Let me give you an example just to illustrate the question. So here I'm looking at equations or polynomials of degree 3, and I'm going to assume that they are generic. I'm not going to explain exactly what it means, but it's just they shouldn't have singularities. They should intersect the boundary, kind of the projective boundary in a generic way. And then the statement is that there are exactly 5 possible shapes that you can get in degree 3, not 6, not 4. There's exactly these 5 shapes that I've drawn here. So again, when I say shape, I only mean up to homeomorphism. These are the pictures that you're gonna get in degree 3. Okay. So you can have just one component like this, you can have one component like this, and another one, a closed component. And well, here are 5 more pictures. So maybe to explain, for example, these 2 ones, they both have 3 components. So they look kind of similar, but they are arranged in a different way. So here I have one component which separates the other 2 components, whereas here I have no separation of the components by another one, which is why I consider them 2 different possible shapes. Okay. And this question, even for curves, and even so already, so degree 3 you can still do by hand, but then degree 5, let's say, already is quite complicated. And Hilbert's question actually was about degree 6. So degree 6 was already a very hard problem. And well, there was a lot of efforts made in these directions. I want to present you one particular technique which kind of revolutionized the field. This was in the 70s, 80s, and this method is called patchworking, and it was developed by Oleg Virov. And this is really a very beautiful method, which is a very nice mixture of geometry on one side and combinatorics on the other side. Because maybe just let's go back one slide quickly. Well, these examples are maybe too simple, but in general, imagine I give you a shape like this, and I ask you to, choose these 10 coefficients that a cubic equation has in such a way that I get a shape which looks like this. And of course, it should be quite clear that this is already quite difficult. I mean, what's the strategy for choosing these coefficients? You have to do it, of course, in a quite clever way. And Virov's patchworking method is a very elegant way of choosing coefficients in a systematic way to get certain arrangements of the topology of the set. So let me very quickly explain to you how this procedure works. So if you don't take away anything from this talk, maybe you at least take away this beautiful patchwork procedure from Virov. So it works as follows. In this example, I want to construct a curve of degree 3. Okay. This is why I start with a simplex of size 3, where each of the vertices of this simplex corresponds to a monomial of the equation that I want to construct. So this would be the constant term, this would be the x term, this would be the x squared term, etc. Okay. Now, additionally, I'm going to choose a subdivision in this case, actually a regular triangulation of this simplex. So here I chose a very simple one. And I will choose a color distribution of the vertices. So I color the vertices in black or white, okay? These colors, really, you should think of them as signs. So you could say that, for example, black vertices correspond to plus, and white vertices maybe correspond to minus, okay? Now I'm gonna do some kind of a combinatorial procedure with this starting data. Actually, I'm gonna produce 4 copies of this picture. And these 4 copies, you should think of them as the 4 quadrants of the plane, okay? And in R2, you have 4 quadrants. This is actually the picture for the positive quadrant of R2. Now we're gonna produce the picture for the second quadrant, okay? So you see what I did? I just took the simplex, I reflected it. I have the reflected subdivision on this copy of the simplex. But you see that the signs actually change a little bit. And I can explain you how they change. So this is basically just reflecting whether a monomial changes its sign when you go from one quadrant to the other one. So for example, let's take this vertex. So we said that this corresponds to the monomial x. And well, here I'm changing, I'm going to the quadrant x is replaced by minus x, okay? So of course, x changes sign, which is why here this vertex has now the opposite color from the color here. So the color flipped, okay? Let's look at this vertex here. This vertex is x squared. Now x squared, when you replace x by minus x, doesn't change sign. So this is why here we didn't flip the colors, okay? And let's do one more example. This one here would be the monomial y. Well, if I go just to the second quadrant, then y doesn't change sign. So this is why it changed. It's still white on the other side, okay? So, well, it's not, I mean, even if you don't quite grasp it, it's just important that there is a very specific, very simple rule for how to change the signs in this copy that I created. And now I'm going to do the same thing with the third quadrant and the fourth quadrant as well, okay? So, well, you see, you can check that I always apply the same rule for changing the signs, but okay, I'm not going to go through it in detail. So now I have these 4 copies, and you actually see that by this rule of changing sign, they agree on the borders of the 4 triangles. So here, they actually agree the colors that I obtain. So I can merge this picture to a single picture, which looks like this, okay? And now, from this picture, there's one more step, which is just, now we're gonna separate the white vertices from the black vertices. So here is the result. So basically, in each triangle, you're just gonna separate the white vertices from the black vertices. And if you do this in each triangle, then you kind of get these branches, this path that when you go through the subdivision, okay? Here I did the same, and here, for example, I have this black vertex which is surrounded by white vertices, which is why I get such a closed curve in this case. And now let's forget about the subdivision and the colors and everything. Let's just keep this red picture. So what we obtained in the end is this picture here, okay? And what Viro, so now the main theorem of Viro is stating that the picture that we obtained in the end from this combinatorial procedure is in fact the shape of a real algebraic curve of degree 3. So there exists some polynomial, some real polynomial of degree 3, such that if you look at this 0 set of this polynomial, it will look like this picture up to homeomorphism. In fact, I can go back to my earlier picture in this example theorem that I gave you, I had this curve. And now you can see what I mean by the same shape. Okay, so it's really only up to homeomorphism. This shape here is the same shape as the shape that we see over here. So by this I mean that we have here these three branches which go from infinity to infinity, and we have this single closed branch, and they are kind of arranged. Well, in this case there is not much to arrange, but they are arranged such that you can construct a homeomorphism from this picture to this picture. Okay. Let me give you one more example, just to, because this one is too trivial kind of. So here is a more complicated subdivision, and again some sign distribution. You do the same procedure. You make 4 copies of this picture. You merge them. You separate black from white, and you get this picture here. And again, now the theorem in this case, this is a simplex of size 6. So now Virchows' theorem tells you that there exists a curve of degree 6, which has exactly this topology, which has this shape. Okay, and this is already a very complicated curve. This is actually one of the famous curves that Hilbert, when he formulated this problem, he missed. He made a mistake. He missed this curve, and it was only discovered 60 years later. So just to illustrate that this is a curve. If I give you this shape and I ask you to give me a polynomial of degree 6 to produce this shape, it will be, if you try it randomly or something like this, it will be impossible to find. Okay, so what this procedure here does for us is it gives us kind of a very intelligent way of behind the proof of this theorem, there is an intelligent way of constructing a polynomial which gives us exactly the shape that we want. Okay. Again, maybe questions till here. I know I'm going I'm quite fast and being quite vague, but I just want to give you kind of a background for what's coming next.
There are no questions yet.
Okay.
Thank you, Johannes.
Yeah. Well, then let's finally go to it's already the last section. So basically I want to tell you about how to think of these pictures in the tropical language. And I should say that, okay, this is a very beautiful procedure, this patchworking technique, but there's one major problem, is that it only works in codimension 1. So it only works for hypersurfaces. It also works for complete intersections, but okay, essentially it's a technique for hypersurfaces, let's say. Okay, and kind of what I want to tell you now is an attempt to generalize at least parts of this process here, this technique, through arbitrary codimensions, and we're going to do this using the tropical language. Okay, so the very general idea of this last section is that I told you before how to tropicalize a family of algebraic varieties to a tropical limit. Okay, and now I don't want to do an upgrade of this process. I want to do a real tropicalization, if you want. So if I have a family of real algebraic varieties, I want to remember some of the real information of these varieties in the tropical limit. And you can, the main idea is already visible from this very simple picture. So here I have, this is on the classical side here, I have a real line, which just, okay, it just looks like this. But okay, if you think about what it is if you remove the places where coordinates are 0, then you see that this line consists of kind of three components. And if you take the logarithm of this picture, then you actually get the amoeba that we saw before, but a bit more precisely, you actually see that the kind of the real points that we have here, they turn into the boundary of this amoeba. And well, each of these 3 components gives one of the boundary segments of this amoeba picture that we saw before. And so it's natural to say that now when we go to the limit, we want to remember, for example, that this ray here it has, well, there is some stuff from the quadrant minus plus converging to this half ray here, but there is also some stuff from the quadrant plus converging to this half ray. Okay, and this idea, this very naive, simple idea, leads us to a definition which, okay, is a bit complicated, especially if you're not familiar with this tropical lingo. But I want to try to, to at least convey the basics of this definition. So from now on, X will always be a rational polyhedral complex in Rn. Okay, so think about it as one of these tropical varieties that we saw in the previous pictures. But it's technically it's a bit more general. You just need a collection of polyhedra which fits together nicely, and the polyhedra should be rational, which means that at least the tangent space, or at least the tangent space of these polyhedra should be defined over the rationals. Okay, and on top of such a rational polyhedral complex, we now going to define what is a real phase structure. Okay, if you want, forget the word phase and just think of it as a real structure. It's supposed to be this additional information that keeps, that remembers some of the real information in my family. Okay, and it consists of the following data. It's just a map from the facets of X. So to each facet of X, to each maximal cell in my polyhedral complex, I'm gonna associate a subset in set 2 to the n, where set 2, I apologize to all number theorists in the audience, but set 2 here means just the field with 2 elements. Okay, so here this is just a notation for set. Well, it's set 2 to the n, and tau means subsets of this vector space. And okay, this assignment has to satisfy 2 conditions. The first condition is actually, here sigma is my name for a facet. So the first condition is that this shouldn't be an arbitrary subset, but it should actually be an affine space tangent to the tangent space of the facet. So this is here I'm using that sigma is rational. So sigma is rational means its tangent space is defined over the rationals, or if you want, over the integers. And so you can reduce modulo 2, and you get its tangent space over set 2. And so this is just a linear space living here in set 2 to the n. And I want this to be an affine space tangent to this linear space. So I want it to be a translation of this linear space. Okay, that's the first condition. I'm going to show you an example in a second. And the second condition is what we call the double covering condition. So what we want is that for each phase tau in my polyhedral complex of codimension 1, so not a facet, but of codimension 1, if you look at all the facets adjacent to this phase tau, and you look at all the subsets associated to these adjacent facets, then you want the symmetric difference of these subsets to be the empty set. So symmetric difference here is the usual symmetric difference. It means you take the union. I mean, let's say for a pair, right? So the symmetric difference of 2 sets is you take the union minus the intersection. So if you write out what this means, it just means that an element, so each element should be contained in an even number of these subsets. Okay, so it cannot be. So for example, a vector in here could be contained in none of these subsets. It could be contained in 2 of these subsets. It could be contained in 4 of these subsets. All of that would be allowed. So okay, this is the definition. I know it's a bit, it's maybe a bit difficult. So let me give you a few examples. Let's start with this very simple example that I used as motivation. So in this case, the limit is just this tropical line. So the tropical line is this polyhedral complex that I'm using. The facets in this case are just the 3 half rays. So to each half ray, I'm gonna associate a subset of vectors in set 2 to the n. And so here, let's look at this half ray, for example. Now, of course, I haven't said this so far, but these vectors, they are just additive notation for sign vectors. Okay. So, for example, the vector 0, 0 corresponds to the sign vector plus plus. So it means it corresponds to the positive quadrant. Okay. The vector 1, 0 corresponds to the quadrant minus plus. Okay. So on and so forth. So using this rule, I just translated what I see in this picture here into subsets here. So for each half ray, I wrote down which of the quadrants contribute in the convergence to this half ray. And what you get is, yeah, you just get these 3 sets. And now let me explain these 2 conditions in terms of these 2 sets. So for example, let's look at these 2 vectors. So here, if you draw this subset in set 2 to the n, then of course what we see is just this line. Okay, it's a line over the field of 2 elements, and we see that this line is tangent to the tangent space of the half ray. Okay, if you look at this part, then what we get is just this line here. And again, clearly it's tangent to the half ray. And then finally, if you draw this subset, what you see here is actually this line. And now, so here, of course, you just have to realize that we're working over set 2. So this line really is the same line as, if you want, like this line here, or, well, it's, you know, it's, so what I'm trying to say is that it's also tangent to this direction. Okay, it's just because we're working over set 2. So this direction, which is the direction 1 minus 1, is the same as the direction 1, 1, which we have here. Okay. So this is the first condition. All of them are affine spaces tangent to the direction of the edge in this case. And now the second condition, the double covering condition, well, it's just saying that each point here is contained in either 0 of these sets. So in this case, it would be 0, or in exactly 2 of these sets. Okay. So for example, just to, if instead here on the third edge, I would use this subset, as in the definition of real phase structure, then this wouldn't work, because here, well, actually, at all the points, I'm now not satisfying the double covering condition. For example, here I have 3 edges, 3 subsets containing the point 0, 0. Okay, so this one is fine. And let me quickly go through another example. So here I have a line in 3 space. So this is a picture in R3 now. Here I indicated the direction vectors of these 4 half rays. And here I indicated the subsets associated to each of them. And if you draw this here, you get, so this, for example, is 0, 0, 1, 0 would be this edge. And now I'm continuing here. And I see this edge. Oops. And then continuing here, you get this edge, and then this last one. Now it's difficult to draw, but it's really this diagonal direction in here. So this would also be a real structure satisfying these conditions. Okay. Now, okay, what's the idea behind these structures? Actually, yeah, maybe first. Let me jump ahead to just a statement about this definition, which might be interesting to some of you, and which is actually important in the theory. So I apologize if you probably cannot well, so I'm not explaining all the details here, but what I want to tell you is that there is a particular class of polyhedral complexes, which are actually fans and which are associated to matroids. So these fans are called matroid fans, okay? And what we actually realized and what we actually proved is that on a matroid fan, the information of a real phase structure is really in bijection to an orientation of the oriented matroid. So in other words, our definition of, well, take a fan and take a real phase structure on such a fan is actually a cryptomorphism for the notion of oriented matroids, okay? Maybe you've heard that these matroid fans have attracted a lot of attention in the last years, let's say, because they gave a kind of a geometric approach to studying matroids, even those which are not representable. You can still study them using the geometry of these matroid fans. And we hope that our theorem kind of achieves a similar situation for oriented matroids. So basically, we're saying that oriented matroids, you can study them using real phase structures sitting on top of matroid fans, okay? But this maybe just as a quick side note. What I really want to tell you about is the relation to this patchworking that I talked before. And to understand this, so, okay, you have to, one more time, be a bit flexible with your kind of geometric intuition. So in a sense, what we want to do now is we want to reverse the process of taking logarithmic coordinates. So before I told you in order to tropicalize, we're going to take coordinates and we're going to take the logarithm of these coordinates. And now essentially I want to reverse this process. Because if you think about it, if you do this for real numbers only, so if you do this for the reals non-zero to the n, you take logarithm, well, then of course on each quadrant, you will actually get a homeomorphism, because logarithm itself is a homeomorphism from the positive numbers to the real axis, okay? So essentially, if you look at this map is just a 2 to the n to 1 map. So the fibers here, each point is just, basically this tells you the absolute value of your point here. And now you just can choose the signs of your point. So you get 1 copy in the pre-image for each quadrant in R star to the n, okay? So you can think about it the other way around. You can say, okay, now I'm gonna think of R star to the 2, which is just a real plane, removing hyperplanes, removing the coordinate axis. So now I have 4 quadrants. I can think of them actually as 4 copies of R2, where each of these copies is, well, it's just the homeomorphic image of this quadrant under the logarithm, okay? And this is what I'm going to do in the following. So I'm going to think of R star to the n as 2 to the n copies of Rn. Each of these copies is just labeled by epsilon, where epsilon is just a sign vector, or alternatively, I'm going to think about it as a vector in C2 to the n, okay? And so what I'm going to do now is, if you give me a polyhedral complex with a real phase structure, I'm going to construct a space which I call the patchwork associated to this information. And this is actually a typo. It should be R star to the n. I'm going to keep it. I was trying to keep it simple, and it's just defined as follows. So in each copy of Rn, which corresponds to one of the quadrants, the quadrant labeled by epsilon, I'm going to take the union of all the cells in my polyhedral complex X, but I only take those cells for which epsilon is contained in this subset epsilon of sigma. So again, I assume that this definition is hard to digest, so let me give you an example. So here is a tropical curve, and I equipped it with a real phase structure already. You can check that this satisfies the conditions of the real phase structure. So now the patchwork is the following. I make 4 copies of this picture. So this is one copy of the picture. This is the next one, just that I reflected it to make it easier to, like for the patchworking story, I'm just gonna reflect it. So here is another copy of this curve. But now in each quadrant, I'm only gonna draw those edges which contain the corresponding sign vector in their subset. So for example, for the positive quadrant, it's associated to the vector 0, 0. And so I'm looking in my curve, I'm looking at only those edges which have 0, 0 in their subset. And well, you see that this produces exactly these 3 edges. Okay. Let's do this for maybe also, let's just do it for 1, 0. For 1, 0, where do I have it? I find it here and here. And so this is why I'm drawing these 2 edges. I just draw it in a reflected manner to make it fit with our intuition, let's say. Okay. So, well, here's an example of a line, which is already difficult to actually, it's kind of difficult to draw because everything is piecewise linear here. So, yeah. But so now I want to tell you what is this construction about? So first, again, I'm sorry, you have to accept a little bit here. So now you're going to restrict to polyhedral complexes, which I call smooth or tropically smooth. And this actually means that locally they look like matroid fans. Okay, so I have defined what a matroid fan is. But in each polyhedral complex, if you fix a point, then locally around this point, what you see is a fan. And I want these fans to be of a special type, namely of this type coming from matroids. Okay. And so what we prove is, first of all, that the patchwork is always a closed chain in homology. Okay, that's maybe not so interesting, but again, you can kind of see it here that there's no sudden stops of this picture. You know, I cannot have like an edge ending somewhere. But the more interesting statement is that if X is smooth, then actually this patchwork that we construct, which a priori is some collection of polyhedra, is actually topologically smooth. Okay. So what I'm saying here is that, for example, let's say on the one-dimensional level, I'm saying that, well, you can get, for example, a corner like this, but this is still topologically, it's smooth. So topologically, locally, this looks like a neighborhood of R. But something like this, for example, wouldn't be allowed. Okay, a 3-valent vertex is not allowed in the patchwork. This is also not allowed because it wouldn't even be closed as a chain in set 2. On a 2-dimensional level, for example, you could have corners like this. This would be allowed because this is again topologically smooth, but you cannot have a picture like this matrix. Okay. But for us, it's a good indication because what is the objective here? These patchworks are supposed to be topology of a real algebraic variety, of a smooth real algebraic variety. And so we're in some sense on the right track because at least what we get here is something topologically smooth. So it is possible that this could be, homeomorphic to a real algebraic variety. And let me just basically state the main theorem. So let me just quickly recall the setup here. So now again, I have X, a family of algebraic varieties over some parameter T. But now I additionally assume that this family is actually defined over the reals. Okay. So actually all my examples before were defined over the reals. It just means that this dependency on T should be a real power series if you want, or could be a bit more general, but let's think of a real power series here. So what I really have here is a family of real algebraic varieties. And okay, I define the limit of this family in exactly the same way as before. So the tropical limit is still what we defined before. But now additionally, I'm gonna equip this limit with a real phase structure, okay? And here is a very quick example. So here I have the polynomial 1 plus x minus y plus t to the minus 1 xy. If you apply the rules that I told you before, you're going to find that the tropicalization of this polynomial looks like the tropical curve that we already saw. So for half rays connected by this bounded edge in the middle. And so now I'm going to additionally equip this tropical limit with a real phase structure, which, well, I'm going to be very brief here, but actually to each facet in the limit, so let's say this edge here is a facet in this case, to each facet I actually have associated a so-called initial variety of this family here. And the initial variety is just given by basically taking an interior point of this edge and putting weights on the variables given by this point, and then taking leading terms with respect to t. So I don't have the time to give you the details here, but if you do this in this particular case, take leading terms with respect to this phase sigma, then actually what you're going to get is exactly the two terms in the middle, x minus y. And then the real phase structure that we associate to this edge is just kind of, I forget about the original equation. I just look at this initial equation now, and I just look at all the possible sign vectors of solutions of this equation. So for example, here, the equation is x minus y is 0. So, well, if x is positive, then y has to be positive. This gives me plus plus, and vice versa. If x is negative, then y has to be negative. So this gives me this sign vector. And now you just translate it into the additive notation, and it gives you 0, 0, and 1, 1. Okay. So maybe not so important the details here, and I have to stop soon. So the main point here is that now the tropical limit can be equipped with a real phase structure. And in fact, and here is the patchwork associated to this real phase structure. This example we already saw before. But the important fact is now that actually the picture that we get here is actually the shape of an element in this family, a fiber in this family, for a t sufficiently large in this case. So here I think this picture is for t is equal to 5. And you see that actually this is a very simple example. Here I have a hyperbola, and this hyperbola is it has the same shape as the patchwork that I've drawn over here, okay? And just to finish, so this is the main theorem. So our theorem says the following: if you have such a family of real algebraic varieties, if the tropicalization of this family is smooth in the sense that locally we have matroid fans, then actually the topology of the fiber in this family sitting inside R star to the n is equal to the topology of the patchwork constructed in R star to the n. So in the end, we have a procedure for kind of a combinatorial way of trying to understand the topology of this real algebraic variety. And for codimension 1, this is just the combinatorial patchworking that we saw before. And I should say that this is more interesting when you compactify it to toric varieties, and this can be done, but I just wanted to keep it simple. Okay, so that's all I wanted to say. Sorry for just using all my time.
Okay. Thank you, Johannes, for your beautiful talk. You have very nice comments in YouTube and the chat on Zoom. We have a question by Diego Alberto, and he say, can patchworking be generalized to higher dimension?
Yes, so the origin. So the original Virus patchworking works in all dimensions, but only for codimension 1. So it will give you hypersurfaces. Okay. But for example, it works in dimension 3, and then you will get surfaces. Okay. But yes, it works in all dimensions. But the purpose here is to have something similar in higher codimensions. And we're not yet, we're not having the full patchworking theorem, but we do have that kind of, under these assumptions, we can actually reconstruct the topology in any codimension from this tropical patchwork.
Thank you so much.
Good.
So we are on time, and thanks, Professor Johannes, for this beautiful talk and for accepting this invitation.
No, you're welcome. Thank you very much. Sorry for not having time to. I see the questions on YouTube, etc.
It's okay. You have a very nice comments, and the talk was very interesting for everyone.
Okay. Thank you very much. Bye bye.
Thank you. Okay, we are on live in YouTube, and for the next talk, we have the Professor Mathilde Lalin from University of Montreal.
Yes.
She's hello, Professor.
Hello.
She is part of the scientific board of this conference, and she will introduce the next speaker.
Yes.
Okay.
So Daniel,
give me a moment, Professor Johannes. You have your screen. Thank you. Daniel, can you try to share your screen, please?
Yes.
Okay, thank you. We are ready.
okay. Okay, so good afternoon, everybody. It's my pleasure to introduce Daniel Labardini Fragoso. Daniel is a full-time professor at the Instituto de Matemáticas de la Universidad Nacional Autónoma de México. He has multiple distinctions and awards. One of them is the recent Cátedra Marcos Moschinsky at UNAM's Física, Instituto de Física, and the Marcos Moschinsky Foundation. Daniel has amazing research projects, and his area of research include cluster algebras, representation theory, algebra combinatorics, and convex geometry. And he will be talking about generic basis for cluster algebras from puncture surfaces. Go ahead.
Yeah. Thank you very much for the introduction and for the invitation to speak here. It's really an honor. So I'm going to talk about a project on which I've been working already for like quite some years, which is about this generic basis for cluster algebras from surfaces with marked points. This is the overall plan of the talk. I mean, here, this part 5, it would be too optimistic to expect that I'm going to have time. So I think it's going to be only the first 4 sections. So let me start with some generalities about cluster algebras. So they were introduced a bit over 20 years ago by Fomin and Celebinsky. And a cluster algebra is defined through a recursive procedure in which one starts with a pair consisting of a quiver, so that is a finite directed graph, which one takes to be two acyclic, and this means that the quiver doesn't have loops and doesn't have oriented two cycles. So two acyclic means none of these two things, but of course there could be cycles of greater length. So there could be longer cycles. Yeah, and one starts with such a quiver and with a tuple of rational functions with coefficients in some field, which one takes usually to be the real numbers. One usually takes it to be the rational numbers, the real numbers, or the complex numbers. Yeah, and then this tuple of rational functions, one just requires it to be algebraically independent. And although I'm writing them as x1 to xn, they are not necessarily the variables for which we write the rational functions. I mean, the x's are rational functions in perhaps other variables to which I'm not assigning a specific notation. So if we start with one such thing, we start mutating it, and by mutating it, I mean performing the following operation both at the level of quivers and at the level of rational functions. So given a vertex, the operation that I apply to the quiver is defined in these three steps, namely every time I have an arrow incoming to the mutating vertex, and one arrow outgoing from the mutating vertex, we add a new arrow, namely this from J to I. That's the first step. So for each pair of such arrows. Now, in the second step, we reverse from the quiver. We reverse in the quiver all the arrows incident to the mutating vertex, and finally we remove oriented two cycles in order to stay in the class of two acyclic quivers, right? And the point is that the point about three is that in the first step, one could have created a two cycle if in the original quiver there was some arrow going from I to J. So it is possible that in the first step one created a two cycle. So in the third step, one has to remove it. Okay, and that's the operation at the level of quivers, and then at the level of clusters, that is of tuples of rational functions. What one does is one replaces the kth rational function. One replaces it with this quotient, which is in which one takes on the numerator a certain binomial formed by taking the product of those variables such that there is an arrow from J to K, and then another binomial where one does the other way around, so that one forms the product of those x's for which there is an arrow going from K to the corresponding vertex I. So let me do an example. So for instance, here, if I only want to mutate at one, if I want to mutate only the quiver at vertex 1, so the first step adds well, sorry about that. So I draw the original quiver, right? And then in the first step, I have to add the composite arrow from 2 to 3. So I add it. In the second step, I reverse arrows incident to K. So I reverse the direction of these arrows. Yeah, and in the third step, I have to delete 2 cycles. So I delete these 2 cycles. Yeah. So this would be the mutated quiver. Yeah, and then if I want to see how the cluster mutation works, so how it works at the level of rational functions. Let's say that I start with this quiver Q and this tuple X. Then when I mutate at 1, well, one can easily check that this is the quiver. But here you see I have to take arrows incoming. So are 3 and 5. So I put up this binomial, and then arrows outgoing. So 1 and 4. So I put this binomial and then divided by x1, right? As in the definition. And x1 gets replaced by that. Yeah, and then if I keep going and then say I want to mutate with respect to 2, then I mutate the quiver with respect to 2. I obtain this quiver, and then this x2 has to be replaced by whatever is dictated by this quiver. So this would be incoming and outgoing, right? But now the point is that there is an outgoing to this one, and so one has to take this one to form the corresponding binomial. So it's kind of a one takes the x1 living in the corresponding in the corresponding tuple, right? So for instance, if I wanted to keep mutating, let's say at 1, then I would have to take certain binomial divided by this thing, right? So it's certain binomial divided by something which is already a quotient, right? x1 and then x2, x4, blah blah, and so on. And then, as you can see, one can really keep mutating as long as we want. And then the cluster algebra associated to my initial information, which consisted only of the quiver and this cluster of algebraically independent functions, is the subalgebra of the field of rational functions, generated by all the cluster variables, that is, by all the rational functions that appear in the process. Right? So I consider all possible rational functions that appear in the process of iterated mutations, and with that I generate something, and then I call cluster algebra that something. And one of the first theorems is that every cluster variable, so that is every rational function obtained in the process, can be written as a Laurent polynomial in the initial cluster. So here, for instance, here, even though when I mutate here at 1, I have to divide by this, somehow some kind of magical cancellations arise, and then the result is a Laurent polynomial in the original one. Yeah, and then from the very beginning of the theory, there has been the problem of finding natural basis for cluster algebras, where this word natural means that a basis for the algebra is somehow natural if it contains the cluster monomials. And by cluster monomial, what I mean is the following. So here at each step of mutations, I have a corresponding tuple of rational functions. So here these ones, here these ones, here these ones, etc. And I can form in each of them all possible monomials in them. So all possible monomials here in x1 to x5, all possible monomials in the elements here, and all possible monomials in the elements here, etc. And I can do this for every at every stage of all the iterated mutations, and all those monomials in all of these different places, I call them cluster monomials, right? So as you can see, it's kind of it's not monomials in arbitrary tuple. It's not monomials in arbitrary tuples of rational functions obtained along the process, but it's kind of all monomials that I can form in each specific place, and then I take all such monomials. And then something that we proved already 10 years ago is that they are always linearly independent. So somehow this notion of naturality for bases of cluster algebras really makes sense. Yeah, and then there have been several proposals. But I would say maybe the most famous ones would be the so-called generic basis of Geis-Leclerc-Schroer, the so-called bangle basis and bracelet basis of Musiker-Schiffer-Williams, but these are only for cluster algebras that arise from surfaces, and the theta basis of Gross-Haken, Kiel, Kontsevich. Yeah, and then of course they introduce these candidates in their works, and then they prove that for certain classes of cluster algebras they are a basis, that for certain class of cluster algebras it's a basis, and they prove that pretty much for all cluster algebras these ones form bases, and then in this case they conjecture that in all cases they are bases. So I'm going to focus on these two types of bases, the generic basis and actually the bangle basis, in the case of cluster algebras arising from surfaces. So let me say a bit about the cluster algebras from surfaces. So the input is a surface with marked points, and by this I mean that this sigma is a compact, connected, oriented two-dimensional surface. So just a kind of a real surface. Let's say a differentiable manifold of dimension 2, possibly with boundary. So like what comes to mind is, for instance, the torus, or I said like it may have boundary, so it may be like the torus minus 1 open disk, and so on, right? So sigma can be any of those as long as it's compact, and M is a finite set of points in the surface, which I call marked points. And then I only require that M has at least 1 point from each boundary component. Yeah, but there can be, of course, points from the interior of the surface, and these points from the interior of the surface I'm going to call punctures. I mean, thinking like like when a tire gets a puncture, it deflates. So in that sense. And then an observation by several authors like Penner, Fock, Goncharov, Fomin, Shapiro, Thurston, is that if one considers triangulations of sigma that have their vertices in M, so the point is we think of M as being prescribed vertices for triangulations, then one can define a quiver in a quite natural way. So for example, let's say that my surface is, let's say, just a hexagon, right? So but that I mean a disk with 6 points on the boundary, so that M consists of 6 points on the boundary, and let's say that the triangulation is this one, let's say. Yeah, and then the quiver, that is the finite directed graph, has the arcs, or in this case the diagonals of the triangulation as vertices, and one draws arrows in the clockwise sense within each triangle. So this would be the quiver, and then that's pretty much That's pretty much the rule for arbitrary t, except that sometimes when t looks very degenerate, one has to make certain technical observations so that this still makes full sense, this quiver. But most of the times, for most t's, it's very easy to draw. And then the next observation is that if two triangulations are related by a flip of a quiver, by a flip of an arc, then the quivers are related by mutation. And what do I mean by a flip? So, for instance, let's go back to this hexagon. Let's say copy. Let me erase the arrows. Yeah, and then by a flip, what I mean is take an arc, erase it, and replace it with the other diagonal of the quadrilateral where it was sitting as a diagonal. So the flip then I would obtain this one. And then of course to this triangulation, I associate a quiver following the same rule that I said before. And then the observation is that the two quivers I obtain are related by a mutation. By a mutation as described before, like the quiver mutation of Fomin and Celebinsky. So this means that we can do the following. We can, let's say, start with this triangulation, and then I have my quiver, and then say, okay, then just take a rational function for each arc, for each of these three arcs. Take one rational function, and then just making sure that in this case the three rational functions you obtain are algebraically independent, and start mutating and start playing the game of mutations to obtain a cluster algebra. And then this property mean the consequence it has is that then I can associate a cluster algebra to the surface, and somehow independent from the triangulation I started with. I mean, this cluster algebra has the property that the cluster variables, that is all the rational functions obtained by iterated mutations as we did before, kind of only algebraically combinatorially, they are in bijection with the arcs on the surface. And then under these bijections, the clusters, so the tuples of rational functions obtained at each step, those tuples are in bijection with triangulations. And moreover, whenever I want to mutate or flip, the two operations really correspond to each other. Another way of thinking about this is that the arc complex of the triangulation is some sort of combinatorial model for the mutation dynamics of this cluster algebra. That would be one way of thinking about it. Yeah, and then we see how to associate a cluster algebra to each surface. Right, and then under this theorem, as I said, like arcs correspond to cluster variables, triangulations to clusters, flips to mutations. So let's say that here I'm considering, let's say that I started with this triangulation. Yeah, and I really, to be consistent with the previous one, I really should add the boundary. So I should really be working this one. Yeah, and then as I said, here I can draw the quiver. Yeah, and then I just pick one rational function for each of those diagonals and start mutating. Yeah, and then when I start mutating, at some point I get the cluster variable corresponding to this other arc. Yeah, and then the Laurent phenomenon of Fomin and Celebinsky tells me that that variable should be expressible as Laurent polynomial in the original ones, and this is the expression. Okay? And then here also, here I'm using the letter lambda instead of the letter x. This is because I was thinking about the part on the Teichmüller space, but yeah. So but what here the point is that here we can see the Laurent phenomenon of Fomin-Celebinsky, right? So this rational function really is the Laurent polynomial, this one plus this one plus this one. Okay. Now let me describe very roughly describe very roughly the Bangle basis proposed by Musiker, Schiffer, Williams, and then they do it by considering perfect matchings on certain bipartite graphs. And then I'm not going to go into full detail because then this would consume it just the rest of the talk. I'm just going to be very sketchy on what the underlying idea is. So here I have the triangulation that I just considered here. Yeah, except that of course when I drew it, I forgot to include the like the boundary. Yeah. Okay. We have that triangulation, and we have the arc that we wanted to express in terms of the original cluster, in terms of the original tuple of rational functions. And then the idea of Musiker, Schiffler, Williams is okay. So consider the triangles that are crossed by your arc, yeah, and then for instance, and then consider, for example, this segment. This segment somehow is opposite to has a side of a triangle as opposite, and so their idea is okay, unfold that that side as if you were playing some sort of reverse origami, as if the original one was already the result of having performed certain folding. So their idea is unfold, yeah, and then of course after unfolding, one obtains more or less this, and then they just write it in a nicer way and realize that what they obtain is a bipartite graph. Yeah. Okay, they realize that, and then they consider the perfect matchings of that graph, so of this graph. And with the perfect matchings, they form a generating function. And the way to generate to produce a generating function is to label the edges of the graph. Yeah, of course, they have a label coming from the original label here, labeling of the arcs. And then with those labels, then for each perfect matching, just take the product of those labels, right? So it would be the product of lambda 1, lambda 6, lambda 4 in this case, etc. And then do this for all perfect matchings. Yeah, so in that case, I obtained this generating function of perfect matchings. Of course, that's a polynomial. So what they do is they divide it by certain product formed very naturally. So here we just look at the arcs that are crossed by gamma. It's 2 and 3. So that's the monomial we form here. And then they consider this expression. And we notice here that this expression is somehow precisely the expression I had before. and this where the expression had been obtained by mutations. Here it's obtained in another way by counting perfect matchings. And somehow that's the construction. And then they define, you see here I have this. And the first thing they prove is that the cluster variables in the cluster algebra, so remember that here it was an X, coincide as elements of the underlying rational function field with this expression that they propose. So what this means is that they see it is that every cluster variable can be expressed using bipartite graphs and considering generating functions of perfect matchings, right? And so what they do is they take this idea and then they push it and say, and what they do is, okay, then they see that for every lamination one can produce a bipartite graph, and for that bipartite graph they can consider the perfect matchings and certain and produce an expression of this form. An expression of that form. And what they do is that they show that if all the marked points of the surface are contained in the boundary, then the expressions they produce using these perfect matchings of bipartite graphs is a basis. And then they conjecture that it's always a basis, even if the surface has punctures, like even if there are some points in M that lie in the interior of the surface. So just for clarity, by a lamination, I pretty much mean a finite collection of a finite collection of non-self-crossing curves that also don't cross each other. And then let's say with certain multiplicities, right? Just indicating that maybe a curve can be drawn several times, disjoint copies. So here it would be some examples of laminations, like this would be a lamination in the annulus, and it's an annulus with 2 marked points in each boundary component, and these are certain this is a lamination in the unpunctured hexagon, and these are certain laminations of this is the hexagon with 1 puncture and the hexagon with 2 punctures. So for each such collection of curves, they can produce, they can define this expression through perfect matchings of certain bipartite graphs. And what I'm skipping is the precise definition of what the bipartite graphs are exactly. Because you can see here there are certain laminations that look kind of crazy, and it's for those. And in that case, I'm skipping the definition, because I want to move on to now give a very rough description of the basis proposed by Geiss-Leclerc-Schroer, called the generic basis. And this is done via representations of quivers. So remember that a quiver is a finite finite directed graph. So a representation, what it does is it just attaches a vector space to each vertex of the quiver, to each vertex of that graph, and a linear map to each arrow. So that's pretty much what it does. And now here, the basic observation is that, well, now we know that each quiver has sorry, and we know that each triangulation has an associated quiver, which here it would be this one, drawn with the rules that I mentioned a while ago. And now the point is, now for each arc, now I have a representation somehow defined in a natural way, a representation of this quiver, because what I can do is say my arc, look at how it crosses the arcs in the triangulation, and for each crossing, put a copy of the complex numbers, and then for each segment connecting those such 2 points, just put the identity between those copies of the complex numbers. So it's defined in a very natural way. And now somehow the idea is, now that we have been able to attach a representation to an arc, is now to try to obtain certain expression, certain Laurent polynomial extracted from the representation, and try to show that it's a cluster variable, and then try to do this process more generally, right? So that one can try to propose a basis, just as Musker, Schiffer, and Williams did, but they used perfect matchings, and now we are using representations of quivers. That's very roughly the idea. But a bit unfortunate is that things do become somewhat technical, in the sense that one really has to move on to consider irreducible components of certain varieties of representations. So with the quiver comes the path algebra. So to the quiver, I can associate its path algebra that has the paths on Q as a basis, as vector space. Yeah, and then once I have that algebra, let's say that I take an arbitrary ideal. For the moment, it's arbitrary. Yeah, and I form the quotient algebra. And now for each possible dimension vector, a dimension vector is just a tuple of non-negative integers attached to the vertices of Q. So of course I can consider the representations that have those dimensions given P, right? And then to think about those dimensions given D is more or less equivalent. I mean, modulo choosing basis is to attach powers of C to the vertices to those dimensions, yeah, and then each linear map attached to an arrow is then encoded by simply a matrix of the corresponding size, right? So we form the representation variety of A for that dimension vector as all those tuples of matrices that give me a representation with those dimensions in the vertices, but also with the property that the ideal J annihilates the corresponding representation. So these ones are for each D. This one is a Zariski closed of an affine space. As such, it decomposes as union of irreducible components. Yeah. And then we consider all possible irreducible components for all possible dimension vectors. And the most technical part is that from the set of all irreducible components of all these representation spaces, namely, then there are countably many such irreducible components for all possible dimension vectors. From that set, one has to extract certain type of irreducible components that I'm not going to fully describe, but it's yeah, that unfortunately I don't have enough time to define in detail. But so the point is, for the algebra, for the algebra I consider all possible representation spaces. I take all irreducible components, and from that set of irreducible components, I take certain subset of irreducible components that are kind of that I mark as special, let's say, and I call them generically tau reduced. Okay. So to each such component, one can associate certain expression, certain Laurent polynomial that one can define by how to say. So the Z is an irreducible component, so its points are representations seen as matrices. And then, so each point is a representation. And so for each such representation, we consider for each such representation, let's say M, which is a point in Z, in this Z. For each such M, we consider the projective, the minimal projective, the minimal, sorry, P0, P1, the minimal projective presentation. And and from this, one extracts certain number. And then one considers from that same M, the generating function of sub-representations. And one calls it Fm. And then with those two things, with the generating function of sub-representations and the minimal projective presentation of M, one forms certain Laurent polynomial, which one denotes then CC A of t M. And when one lets M vary in this Z, which is a variety, one can prove that Z has a dense open subset where this takes a constant value. And then one defines this one as the generic value taken by these CC functions. Then again, it's a bit technical, and that is why I'm skipping the details. But my point is that one can to each irreducible component here associate a certain Laurent polynomial, which would be the analog of the Laurent polynomial associated by Musiker-Schiffler-Williams to a bipartite graph. Okay, and now the point is we know that each triangulation has an associated quiver. Yeah, and then something that I noticed in my PhD, and then other people too, and then with different levels of generality, and then something in progress is that sorry, this is not, sorry, this is for some other result later. Something that I noticed in my PhD and this other group of people simultaneously and independently is that one can define not only a quiver, but actually an algebra in a natural way by taking the quotient of the path algebra modulo the ideal generated by, in this case, the paths of length 2. Yeah, and then the paths of length 2. Well, the paths of length 2 contained in the triangles. So yeah, and then this in the case where all the marked points belong to the boundary. When there are no punctures, when there are punctures, it's a lot more complicated. But the point is, there is an algebra attached in a natural way to each triangulation, not only a quiver. And each lamination gives rise to a module over such algebra, and somehow the way each lamination gives rise to an A module is pretty much the same idea, follows pretty much the same idea that I described before, which is that every time one crosses the arcs, one puts a copy of the complex numbers, and then one puts the identity for each such segment. So here it would be the identity. Yeah, except that one has to take into account the kind of the technical definition of what a lamination is, and then perform certain combinatorial moves before attaching this representation that I had already described. So here there's one more example, like for instance here, it's the annulus with one marked point on each boundary. Here is the triangulation consists of these two arcs, and then here I have this lamination, and then the representation looks like this. Okay, so each lamination gives rise to an A module. And then what we have proved, so Guys, Schroer, and myself in 2020, in the case when the marked points all lie in the boundary, and with Christoph Geis and John Wilson in the case of in the possibly punctured case. So here is punctures allowed. We prove that if the boundary is not empty, but of course punctures allowed, this representation, which was the obvious representation that I had in mind from the beginning when I started talking about representations, belongs to one of those irreducible components, and this irreducible component is one of the special ones that I picked up. And then what we had proved with Geis and Schroer is that the set of all possible CC functions of those irreducible components is a basis for the cluster algebra, and it's independent of the triangulation used. So in other words, if you give me another triangulation, then of course I have the corresponding representations of the other algebra and so on. But in the end, as elements of the ground field of rational functions, they give me the same set. Okay, so we prove that, and here I have to say we rely on very strong results by several people to be able to prove this. And what again, Geis, Schroer, and myself proved in the unpunctured case, and with John Wilson in the case of punctures allowed. So in the case when there are marked points in the interior of the surface, is that this set, which is the so-called generic basis proposed by Geis, Leclerc, Schroer, coincides with the Bangle set of Musiker, Schiffler, Williams. In other words, these Laurent polynomials that we produce using the geometry of the representation spaces of the algebra coincides with the basis. I mean, those elements coincide with those expressions obtained by Musiker-Schiffer-Williams as generating functions of perfect matchings on the bipartite graph that they assign to the lamination with respect to the given triangulation. And then as a corollary, we obtain that indeed this Bangle set proposed by Musiker-Schiffer-Williams is a basis in the case of punctures allowed, because they had proved it when also in the case when all the marked points were contained in the boundary, but they didn't quite prove it in the case of when punctures are allowed, and now we are obtaining that as a corollary of this result, and of the fact that we already knew by them the previous work with Jan Schroer and Christoph Geist that the generic basis is a basis. Okay, so it seems that I still have some time. So here maybe I have to stop and ask if there are any questions. Yeah, or if you would like me to say a little bit about the motivation, a little bit like...
Daniel, you have 5 minutes more.
Yeah, okay. Mm-hmm. So, okay, so the one motivation for considering these cluster algebras associated to surfaces is that those cluster algebras arise naturally as some sort of coordinate ring of Teichmüller spaces, or more correctly, of decorated Teichmüller spaces. So let me go maybe very quickly. We consider the Teichmüller space of ideal polygon, of let's say of ideal n-gons. Yeah. So an ideal polygon in the Poincaré hyperbolic plane. So it's let's say it's the hyperbolic plane, and this is the Poincaré model. And then an ideal polygon is really determined by its n vertices at infinity. Yeah, and then an ideal polygon with marked vertices is such a choice of such a choice of n vertices in the n ideal vertices, but just with ordered in the clockwise order and with a first element. Yeah, right. So that I know that there's a first element, second element, third element, fourth element. Okay, so that's the Teichmüller space modulo the group of orientation preserving isometries of the hyperbolic plane. So modulo the Mobius transformations that preserve the Poincaré disk. That's the Teichmüller space, and then we decorate it. And so the decorated Teichmüller space consists of points. Its points consist of an ideal, a point in the Teichmüller space, and then a choice of horocycles at each of the vertices. So not only of the tuples of vertices, but also of a choice of choices of horocycles based there. And then given a point there, so I have for each pair of vertices, I have the corresponding horocycles in the decoration, and then I can cut it. I can consider the full geodesic, the full hyperbolic geodesic connecting the vertices. I can cut it. I can measure it. I mean, I can measure how long its hyperbolic length, and take this expression, which is pretty much, I mean, this is the exponential. So this is pretty much the square root the is sorry, this is pretty much the hyperbolic length. It's almost the exponential of L of L divided by 2, except that one has to take a certain signed version, depending on whether the horocycles cross each other. Sorry, depending on whether the horocycles cross each other or not. Okay, the point is, for each diagonal, then what I just did is produce a function from the decorated Teichmuller space to the positive real numbers, and then in the space of all real valued functions on the decorated Teichmuller space, that the ring generated by all these functions that I just produced by measuring geodesics forms a cluster algebra. So the for each polygon, when I consider its decorated Teichmuller space, one can define certain type of coordinate ring that has the structure of a cluster algebra. Yeah, so I think I'm going to stop there because I am running out of time. So yeah, thank you.
Okay, so we thank Daniel for this very interesting talk. Are there any questions? Okay, I don't see. Are there any questions in the YouTube? I didn't.
No, in YouTube there are no questions.
Okay.
But I have a quickly general question for Daniel.
Yeah.
And it's about recommendation. If a student want to learn this topic, what bibliography do you recommend to start?
Right. So there is, yeah. So there is some chapters of a book in the writing that by Fomin, Lauren Williams, and Selevinsky that can be found on the archive. So if maybe even if you just Google this, there's going to pop up in a book that they are writing and whose chapters are available in the archive. So maybe that's where I would start, for motivation on sources for cluster algebras. That's I think maybe where I would start. Yeah.
Thank you so much, Daniel.
Okay, so if there are no other questions, we'll thank Daniel again.
Thank you for listening.
Okay. Thank you, Daniel, and thank you, Professor Matilde, for your support, and Daniel for accepting this invitation. We are on time for the next talk. And for the next talk, we have the Professor Matilde Lalin, and she is professor. No, I'm sorry. Is for the next talk, we have the Professor Sonia Trepue, and she is first president of the Mathematics Union of the Argentina, and is professor at the Universidad Nacional de Mar de Plata. She will be present the next speaker.
Wait a minute. Okay, here I am. Well, it's a pleasure to me to introduce Maria Ofelia Ronco.
Professor, let me see if the Professor Maria Ofelia can try to share her screen.
Okay, I shall share my, okay.
Okay.
A view and then I think, oh, sorry. Okay.
Okay. 30 minutes.
Yeah.
Okay. Can you see it?
Yes, thank you so much.
Okay. We are ready?
Yeah.
Okay. It's a pleasure to me to introduce Maria Ofelia Ronco. Maria is a full professor at the University of Talca. She has been participating in the organization of several meetings, in particular the 23 Latin American Colloquium on Algebra, and she has been a plenary speaker in different mathematical events, in particular in the second meeting of Women Mathematicas of Latin America. Also, she appears in the book Retratos de Matemáticas, Entrevistas a Mujeres Matemáticas de América Latina y Europa. Her research area is algebraic homology and algebraic combinatorics. And the title of her talk is Primitive Elements for Magmatic Infinitesimal B-Algebras. Okay, go ahead.
Okay, thank you very much, Sonia. What I'm going to talk about is just a problem that, I mean, this meeting of women, Latin American women in mathematics, we had some groups and we had people who didn't work in the subject, and we have to give some problem and try to solve it with them. So what I'm going to talk about is the problem I gave to Uruguayan colleagues, Dalia Artestein and Ana Gonzalez. So it's very simple. I will just recall the basic definitions and then go to the problem. We wanted to study large combinatorial Hopf algebras introduced by Vivian Pons and Vincent Pilot, and which were very, very difficult to generate, okay? So what I'm going to, I mean, I suppose most of you know the definitions, but I recall it just in case. So you know what is an unital algebra, and you know what is an augmented coalgebra. It's just the dual notion. So you have some map from, A into A tensor A and a co-unit. And a bialgebra just have on the same vector space an algebra, an associative algebra structure, a co-associative coalgebra structure, and you need that delta, I mean the coproduct and the co-augmentations are algebra morphism. And well, this is what, I mean, I will use it without saying. We use all the time, which is called the convolution product of a bialgebra, which is just defined, you take delta, then you multiply two morphisms, and then, it's that. I think it's, so the endomorphisms of H are just, and with this product, the convolution product is just an associative K-algebra. So, well, examples of Hopf algebras. I mean, a Hopf algebra formally is a bialgebra which is equipped with an endomorphism called the antipode, which is the inverse for the convolution product of the identity. But we have essentially, for me, two groups of Hopf algebras: the group algebra, which is quite well known. You have the product, and the diagonal of an element in the group is G tensor G, and the cotensor algebra. You take a vector space, you take the tensor space over it, and then the coproduct is just the deconcatenation. So you broke a list of vectors into in all the ways by preserving the orders. And if you want a graded product in this coalgebra, you just, I mean, and you want a Hopf algebra, then you need to put the shuffle product. So you take two vectors, you just concatenate, but then twist them, the product under the action of the shuffles. Okay, so this is very classical, and normally in characteristic zero, you get a lot of Hopf algebras, which are the same direct product of a group algebra and a quaternary algebra. My examples will always enter in the second example, but okay, so in a Hopf algebra, you have the group-like elements, which are the elements that such that delta is x tensor x, and the primitive elements, which are the elements such that delta dx is x tensor the identity of the base field plus the identity tensor x. So whenever you have primitive elements, you know that H is just the augmentation ideal plus a copy of K. So the idea of studying the Hopf algebra is just to study the kernel of the augmentation. And you have a primitive filtration. F1 is the subspace of primitive elements of H, and then Fp are the elements such that delta var for me is the reduced diagonal. It's just the diagonal minus x tensor 1 plus 1 tensor x. And you need that each piece is in the filtration below. So we say that H is conipotent when the augmentation ideal, the augmentation ideal is just a union of this filtration. So all my examples will enter in this last case. And any conipotent bialgebra is a Hopf algebra, actually, because you can construct S as a series. Which conipotence means is that the convolution product, if you use the reduced diagonal, will vanish at the moment for any element. So you may develop any analytic functions in this bialgebra, and you just, to construct it, the antipode, you just develop the function x, the inverse x power minus 1. So for this problem, for me, bialgebras and Hopf algebras are the same for my examples. Okay, so let me say this is a very, very classical result. So if you have a Lie algebra, you know that the universal enveloping algebra is the quotient of the tensor algebra. So you just have a functor from associative algebras into Lie, and you consider, which is just the Lie bracket is the anti-symmetrization, and then you take the free associative algebra over Xi and divide by the relation, which means that the bracket in Xi is the same as the bracket in the associative structure of T of Xi. This is a very easy way to construct a left adjoint to any forgetful functors. So you can do that. And what the Cartier-Milnor theorem states is that when you are in characteristic 0 and H is conipotent and co-commutative, is the same thing to study Lie algebras than its enveloping algebras. Okay, so you can recover all the bialgebra structure from the primitive elements, which are Lie algebra. I didn't put it, but the bracket, the primitive elements are closed under the bracket, the Lie bracket. So, okay, there is some point in Milnor's Moore paper that they do not work on associative algebra from the beginning. So they say, okay, if your product is not associative, so you have no more a bialgebra, but just a co-commutative and a co-associative co-product, but some product which satisfies a priori no relations, then the associator of the product will be also, the primitive. I mean, the subspace of primitive elements is closed under the associator. So you get 3 array operations on the primitive space, on the space of primitive elements of H. So we went for there, and this is for let's say bialgebras, and I want to introduce another type of relation. I mean, in the bialgebra, the relation is that the coproduct is a morphism for the product. Okay. Now, I want to ask to say which is a unital infinitesimal bialgebra, and the reason we introduced that is the following. There is a paper of Hans Bauers, Invenciones, which speaks about the double Kovar construction, and he introduced the notion of B-infinity algebra. So a B-infinity algebra, you say B has exact, you have a graded differential space. I didn't put a Bn there. So you have a graded, differential graded vector space, and you say that it is a B-infinity algebra when you have formal deformations of the cotensor algebra over B. Okay, so that means that you have a product on non-graded now, okay, because graded you have only the shuffle, and a differential map which satisfies, well, that the concatenation coproduct is an algebra morphism for star, the differential is a co-derivation for the coproduct and a derivation for the product. So when you just look, what does it mean? You understand that just these two relations mean that the product is defined by a family of M-array products, okay, that define quite complicated relations, because you need, I mean, this condition I means that the product is defined by this family of products, but you also need to be associative. So it gives awful relations of the M. And again, I mean, what D defines is more or less an A-infinity algebra. So you have a family of maps, and the derivation D is given by this family of maps. I just write down 2 formulas here. So I say what B star W will be reconstructed. You have the shuffle, which belongs to B tensor 2, and then one element in B, which is the M11 BW. And for 2, you multiply B1 tensor B2 by W. So you get again the shuffle, which is in B tensor 3, plus B1 tensor M11 B2 W, these 2 elements which are in B tensor 2, and an element in B. And you may go on and construct them. I mean, it's not nice, but you can you may construct them by hand. So at the moment we wanted to understand if it was possible to construct an enveloping algebra for a B-infinity algebra. Okay, this was our problem with Jean-Louis a long time ago. So let me point out something, is that M11 is what is called a Lie admissible. I mean, it's not associative or pre-Lie, but if you antisymmetrize M11, you get a Lie bracket. It's called Lie admissible, just like that. So we wanted to do some kind of enveloping algebras for these B-infinity objects, just because, I mean, you see, B-infinity objects are very, very complicated, and you want just to know the free object, I mean, which is a B-infinity algebra spanned by vector space, the dimension, the representation of these objects. So we had to introduce something. I mean, you have a product, you have a Hopf algebra, but you need to add some product. And the relation between delta, which will be normally the deconcatenation, but not necessarily, is this relation that I put there is almost a co-derivation, you see, but you have this term which change the minus x tensor y, and this you need to do that to get units. So what we prove at this moment, I mean, is that any conipotent infinitesimal bialgebra is isomorphic to the cotensor algebra over its space of primitive elements. And which is more or less interesting is that you have a functor from, okay, I'm going to a bit too fast. So what I call a differential two associative algebra is a vector space where you have two associative products with no relation between them, and the differential satisfies that D is a derivation for a star. Again, when you define a bialgebra in this context, you just ask delta. I mean, you have as H star delta and D to be a differential graded bialgebra, and you ask D to be a co-derivation for delta and a derivation for a star, and that point delta is a unital infinitesimal bialgebra. Just the relation I put below. So when we do that, we may construct a functor, which is a forgetful functor. I mean, you keep the same vector space, and you may construct all these products and all this Dn on any differential two associative algebra. And so you may construct the left adjoint. You take the free differential two associative algebra, which is not very difficult to construct. And then you divide by the relation, say that the infinity operations are the same on both sides, and you get some kind of enveloping bialgebra for that. And you say, well, okay, the theorem is that any conipotent differential two associative bialgebra is isomorphic to the enveloping algebra of its B infinity algebra of primitive elements. So you get more or less the same result than Milner-Moore but in this context. So you get for free, more or less, the free B infinity algebra over any vector space. So now I can, this is the reason why we introduced these infinitesimal unital bialgebras. And afterwards, I mean, there are many, many examples of them, essentially on what is called a combinatorial Hopf algebras. I mean, a combinatorial Hopf algebra is a Hopf algebra which is graded, and in each degree you have a basis. I mean, a combinatorial set basis, and you work there. Well, so there are many, many. I mean, you have combinatorial Hopf algebras of surjective maps, of permutation is the Malvenuto-Reutenauer Hopf algebra. We define one on planar binary rooted trees. There exists another one on planar trees, and on, okay, and let me say there are another one for knot theory defined by Traev. This is the Kons-Kramer Hopf algebra, which is also a combinatorial Hopf algebra. And we wanted to study a large Hopf algebra. It's the Hopf algebra of integer relations introduced by Pilot and Pous. So this is a large Hopf algebra. It contains the Malvenuto-Reutenauer algebra as a subalgebra, the Hopf algebra of planar binary trees, the Hopf algebra of partially ordered sets, special partially ordered sets. I mean, there are many, many Hopf algebras that can be studied as subalgebras or quotients of these Hopf algebra. So, well, what is an integral relation? You have the set 1n, and you consider all the reflexive relations on these sets. I mean, it's all subsets of the Cartesian product of n by n. So you consider the vector space, which is spanned by all these elements, and the Pilot and Pons put the Hopf algebra structure there. Moreover, Pilot, they have defined previously an order on this which extend the Bruat-Wick order and the Tamayo order. And they show that the product in this algebra is induced by intervals for this Tamayo order. So it's a very, very large paper, this Hopf algebra. And so we wanted to understand how to generate these algebras, how to describe this large Hopf algebra. So the situation is the following. We need to work not with associative. I mean, our first point was to generate this algebra by certain products. I mean, you have in R1 only one element, which is the point, and the relation is a trivial one. So then you need to generate all the vector space, but some operations. We have some associative operations. I will describe them after, but we cannot, at least we couldn't, generate all this vector space with associative products, but we did it with a magmatic one. So a magmat for me is something which is a binary product satisfying nothing a priori. So we extend the definition of infinitesimal unital to magmatic, which is exactly the same definition, but you don't ask the product to be associative, and you consider when you have a family of products, okay? I call them star S. So we say, okay, I am considering a vector space, a family, eventually infinite family of generators, and a delta which satisfies with any product this relation. And I want to study it, to understand it, like saying, well, it's either the symmetric or the tensor coalgebra of its primitive part. What can I say about the primitive elements of this bialgebra? So we began to study the free object for this. And this is very, very easy. I mean, you must consider all the set of planar binary rooted trees, and you must color, okay, by S any node, okay? So it's not the same that the algebra of planar binary trees we defined with Lode, and essentially which was a subalgebra of permutations, because you are changing the degree, you are shifting the degree, you're counting the leaves, not the number of vertices. So you have very easy operations there. The wedge of two trees is just you join the two trees to a new put, okay? One on the left, one on the right, and the it's graded for the number of leaves, you have no problem. And the second product, essentially, if you take T, okay, you make the wedge of T with the bar, which is the element in degree 1, and then you just join it to the first leaf of W. So these two operations are quite natural, and we want to use them to define the primitive elements there. Okay, so we consider we color the vertices. If you have n leaves, you have a -1 vertices, and you make color and take the product. And just the S product is you take the two trees and in the roots you put is. Okay, so this is the star S. And okay, this is the free magmatic algebra over one generator. Okay, so if you have more generator, you just have to color the leaves. It's not very complicated. So when you do that, you say, okay, I want to define a coproduct. I want to give a bi-algebra factor there. And so it's very easy because if it's free and you ask delta of the bar to be one tensor, the bar plus the bar tensor one, you have only a unique way to define delta. So you define it, and the result, I have done it here, it's just, I don't know if you see my hand, but what you have to do is read this for reduce. So you have not the trivial elements. You just cut the tree at all the vertices, and you take off this color, okay, if it's color, and you take the coproduct. So instead, okay, well, I'm not going to speak about other Hopf algebras because you are not supposed to know that, but you just cut in each vertex, you redress the tree, and you take this difference. It's not very complicated. And there is some, maybe you are interested. So our delta has, of a tree, you have one element in each dimension, one element in the basis. So you can shift the delta, and this delta is an infinitesimal bi-algebra, non-unital in the sense of Johnny-Roth. So there are some operations that we may perform on umbral calculus and other constructions, and we may just shift big delta into small delta, and we get a classical infinitesimal bi-algebra in Johnny-Roth definition. Okay, so now what we want to have a big magmatic infinitesimal bi-algebra, and we want to compute the primitive elements. So what we did is the following. We recover an old paper of Marcelo Aguiar and Frank Sottile, where they do the following thing. You have the trees, the planar binary trees are for each n are planar ordered by the Tamari order, and they consider the Möbius spaces of this vector space. Möbius spaces is we take a 3T and you consider the sum for W smaller or equal to T of the Möbius function WT multiplied by W. So this is a change of basis in the algebra spanned by all planar trees, and they consider either for Malvenuto-Reutenauer, which is a bit different, but no matter, or for the algebra of planar binary trees, they prove the following formula. So they prove that delta of the Möbius base, an element in the Möbius basis, is the sum from T1 over T2, means that T1 is glued to the first leaf of T2. So when you take all the possible ways of writing T as the gluing of T1 and T2, and this is the formula. So in particular, they describe all the primitive elements of the, the Malvenuto-Reutenauer, they took permutation, that is more or less the same trick, and of the algebra of planar binary trees with the other degree, the other one. Because if you have a tree which has a bar, wedge, another tree, this element gives M the T is primitive. And this is a basis of primitive elements. So we wanted to recover in our algebra, which is different because we changed the degree, changed the coproduct, etc., the same result. And we are going to replace the bar by the bar with a small feet, which small foot that we defined previously. So, sorry. Oh. Okay. So for this, we have to prove, and I put this because maybe it's interesting for someone working on combinatorics. I mean, the Möbius function of the ternary order is quite known. I mean, you have many formulas to compute it, but we get a way to compute it for using just our two operations, the wedge and the over. And so 1Tn is the largest element for the ternary order, is the comb on the right side, and 0 is the comb on the left side, the smaller element for the ternary order. And we may compute all the Möbius function using these two algebras. So I give the formula. It's not very interesting, but it's quite technical. But it's just as far as we could find is original. I mean, it's a particular way to compute the solution. Okay, so in this context, we prove that we have the same formula for our bialgebra of planar rooted rings, except that our algebra is not a bialgebra, it's magmatic, and we color any vertex by a small s. And so we have for an S magmatic algebra, and we get this formula. So we know, I mean, these elements are primitive. If you color them by a fixed list family of S, we get the primitive elements of this algebra. So, okay, so we say, okay, which are the primitive elements? We have first one, if you have two operations, S, you fix an S0 in an S, and for any S, you have the difference, and this is always primitive. So this is the first, I mean, which replaces somehow the bracket for us. And then you take all the Möbius elements, which are like operations on any S magmatic bialgebra, which are of the weight the bar, wedge, another tree. So this spans, I mean, they have a subspace, and this subspace is precisely the subspace of primitive elements in the magmatic algebra. So, well, we have previous result for magmatic algebras. We proved quite a long time ago with Jean Villaudet and Ralph Holtkamp that any Cornell-potent unitary infinitesimal magmatic bialgebra is also isomorphic to the cotensor algebra. The cotensor comes, I mean, the co-associativity comes from the coprolate, so it's no problem. And so you just need to compute the primitive elements. Well, now you consider what I say S0, and you get that if S is no empty, you get, you know, I mean, your bialgebra will be isomorphic to the cotensor algebra of its primitive elements. And what we prove is that, in fact, this is, I mean, the primitive elements are completely covered by the elements generated by the Möbius elements, so Ki. So this is our general theorem for the primitive elements, and we may describe the whole magmatic algebra. This is in general, I mean, this is for a free magmatic bialgebra. Okay, now what we need to study Pilot-Pons bialgebra is just, you know that any magmatic bialgebra will be the quotient of the free one. So what we need is to generate all integral relations by some operations. To find generators, you consider just the the unique element of relation on one element, and then you need to span all the vector space with these operations, and you need them to be magmatic, which means nothing, and just to verify with the delta the infinitesimal relation, unitary infinitesimal relation. So, well, the remark is the following: you have, I mean, if you have two integer relations, you may take just the disjoint union. You may say, okay, I take all the pairs E, she, where E is in R and Q is in the last elements. You may done the other way around. So you take all the pairs she, I, where she is in Q and I is in R, or you may take both of them, which does not appear, but okay, I call them down, up, down, arrow. So you take all these elements, and these are associative products, but they do not generate the whole vector space. So what we need is to introduce smaller space. So if you fix R and you consider, I mean, you have this set of operations, and you just relate. You take R and you take Q, and you use alpha to relate the last elements of R by just the first element of Q. So these operations suffices to generate the whole algebra. But again, they are infinitesimal, they are, but they are not associative. So they are just magmatic, okay? But okay, we did it. I mean, I don't know, it's a bit, I'm going a bit fast, but the definition is, you can imagine what it is. So, I mean, you have the last elements of R, you look alpha of this element, and you relate it following which alpha says to the first element of Q. And okay, so you say, okay, all this map is generated by these elements, and these elements satisfies this product star alpha satisfies the unitary infinitesimal relation with respect to the product delta R. So now you may apply the theorem. I mean, I do not pretend that this, like as a magmatic algebra, K of R is free, but it's a quotient. So if I know the primitive part of the free, I know the primitive part of the primitive elements of K. So, well, what we get is that, in fact, H is isomorphic to the potential coalgebra, and over prim, and prim is generated just by this by applying these Möbius elements in all the nodes, and you have to decorate, I mean, all the nodes by the product of star. So this is, I mean, I was a bit fast, but I think it's more or less what I wanted to tell you. There, if I have some time, I mean, which is quite interesting, because I'm saying what, I mean, I'm telling you the results which work, but there are many ones that do not work. And our main interest was not on relations, on integer relations, but it's just subsets of n cross n, but on special partially ordered sets, order sets. I mean, there are sets which have two orders, one total order, so you can enumerate all the elements, and a partial order. And you may restrict all these to the algebra generated by this type of process. There are many works. I mean, you have two Hopf algebra structures there. One is the Pilot-Pons, and there is another one defined Malvenuto for C, which uses the items of the process. They are different, and well, we are just trying to work with them. And in this case, there is, I mean, you may apply the same thing, but you cannot generate the whole vector space easy. I mean, it's an open problem to generate from the one element all the other sets. So we get a family of primitive elements, and we have still some other, I mean, okay, if you apply the result to algebras which are well known, like Malvenuto Rettenauer or the Algebra planar binary trees, we get what we had before. But there are some spaces of triangulations which are subalgebras, sometimes quotients of this algebra of integer relations. And well, we have, I mean, sometimes you get good results. We are trying to to write down that, but not always. Okay, the problem of generating all the space, even for a subalgebra or a quotient, is not evident. And now, okay, I'm finished. I'm done. Thank you.
Thank you. We thank Maria for the very nice talk. There are any questions, remarks? The chat.
So I am trying.
Thank you, Maria.
Shanique, do you want something? Sorry, I'm.
Can I ask a question?
Yeah, sure.
Hi, Maria. Thank you for your nice talk. I have a little question about the monomial bases that you have in this magmatic context. Do you have you work on formulas for the product of the monomial bases?
The product. Well, you do not have, I mean, okay, let me say, we are working on the dual of Pilopons, but this is not important. Their product is just the shuffle of taking the arrow product. So we add a lot of products to generate everything. Yeah, maybe for the product, or I mean, if you take, we have the products up arrow, down arrow, and up down arrow, and even the disjoint union are infinitesimal, unitary infinitesimal with the delta. But these products, they are associative, you may shuffle them, so you get 4 Hopf algebra structures, okay? And we have not looked at it, because our problem was to generate, and they do not suffice to generate
Sure.
Okay.
I'm asking because I know it's not trivial to get the formula for this product, even for the Lodey-Ronco case and Malvenuto Rettenauer.
No, yeah, you have to choose what you put in the product or in the product, and this one which
Sure.
is no, it's always the same problem,
Sure. Thank you very much, Maria.
What I'm saying is also interesting is that the methods we use to construct a Shoni-Rota infinitesimal by algebra using this coproduct, the small delta, you may apply it to any, I mean, all the examples I know of the combinatorial of algebras.
I see.
So
Thank you, Maria.
Something more to discover there. Yeah, welcome.
More questions? Remarks? Well, if not, we thank Maria again for the very nice talk. Thank you very much.
Thanks to you, and I'm sorry I have to give classes, so I'm going to leave your talks. We are very, very interesting, but I have. Okay. Thank you very much for the invitation. Bye.
Thank you.
Thank you, Professor Maria and Professor Sonia, for your support and for accepting the invitation to be part of this conference. And now we have a little time for a break. So the next talk is in 50 minutes. So maybe it's a good time for go to coffee or something like that.
Okay.
Okay, thank you very much to all the participants for connecting. So it's my great pleasure to introduce our next invited speaker, Professor Christine Lauter. Let me say some words about Professor Lauter. After graduating from the University of Chicago, she was an assistant professor of mathematics at the University of Michigan, and then she continued her research activities in industry. So she worked at Microsoft Research during 22 years, where she was the head of the cryptography group, and is currently a researcher at Meta EA, where she's the West Coast director of the research science at FAIR. She's a co-founder of the successful Women in Numbers Network, a research collaboration community for women in number theory, and she has been the president of the Association for Women in Mathematics in the period 2015-2017. She's a fellow of the American Mathematical Society, the Society for Industrial and Applied Mathematics, and then the American Association for the Advancement of Science in the section of mathematics. So thank you very much, Professor Lauter, and let's enjoy the talk, her talk about salsa picante verde, machine learning attacks on LWE with small sparse secrets. Thank you.
Ok, muchas gracias por invitarme, muchas gracias por estar aquí conmigo. Estoy muy contenta de estar con ustedes. Lo siento, pero voy a dar mi plática en inglés porque no sé todas las palabras en español, pero mucho gusto estar aquí en esta conferencia muy bien organizada. So I'll switch to English now. Thank you so much for joining me. I think the captioning is better at understanding me in English too. I wasn't doing a very good job in Spanish. So I'm going to talk about some new work that I'm very excited about, salsa picante y verde. So for non-Spanish speakers, this is spicy green salsa, but I will explain what it means a little bit later in the context of mathematics. So I'm going to talk about machine learning attacks on post-quantum crypto systems. Thank you so much for the introduction. So I don't need to say more about myself, but I am the director of all of FAIR Labs North America now. And I'd like to point out, I'd just like to mention that we are always hiring researchers. So we actually have excellent programs for to hire interns. So graduate students working in AI throughout Latin America as well. So you should think about, if you're a graduate student, you should think about our internship programs to come and work on AI research at FAIR, at Meta. And FAIR it used to be Facebook AI research, but now it stands for Fundamental AI Research. So we're the AI research wing of Meta, the company Meta, which used to be Facebook. We also have programs, we have joint PhD programs with a number of universities in North America, including University of Washington, NYU, Carnegie Mellon, Berkeley, UC Berkeley, and NILA, University of Montreal in Montreal. And we also have AI residency programs for students kind of before entering a PhD program. And we also hire postdocs and visiting researchers. So please look up the opportunities for coming to join us to do AI research at FAIR. So the work I'm going to talk about today is essentially part of three different papers, salsa picante y salsa verde, which is joint work with a number of authors who are all listed here in alphabetical order, not separated by the papers. So in this talk, I'd like to talk about algebraic systems for post-quantum cryptography. But first, let me just mention pre-quantum cryptography, meaning the cryptography we use today is based on algebraic and number theoretic problems. So RSA is based on the hardness of factoring large integers. Diffie-Hellman is based on the hardness of discrete logarithm problem in the multiplicative group of finite field, for example. ZP star or FP star. And elliptic curve cryptography is based on the hardness of the discrete logarithm problem in the group of points on an elliptic curve. So all of these are examples of algebraic or number theoretic problems which are used for cryptography, which as it is deployed worldwide today. So I was at Microsoft Research for 22 years, and I worked on all of these systems and getting them deployed worldwide. They form the foundation for secure communications and e-commerce worldwide, and are very, very important. So the issue is that with the advent of quantum computers, all of these currently deployed systems today will be vulnerable to very efficient attacks, polynomial time quantum attacks, once a quantum computer can be built at scale that can do computation faithfully without, losing too much accuracy. And so these systems will essentially be broken. RSA and ECC, for example, will be broken once we have a full-scale quantum computer. Now, we already have, examples of small quantum computers today, but we do not have full-scale quantum computers. So it's important to note these systems are not broken yet. But in order to be prepared, the NIST, is the National Institute of Standards and Technology in the US, launched an international competition from 2017 to 2022 to standardize schemes for post-quantum cryptography, and concluded last year in 2022 with some recommendations. So one of their recommendations, several of the schemes that were standardized were based on what's called lattice-based cryptography, which is also an algebraic kind of structure, which also has some number theory behind it. So the way I've structured my talk today is that I'm going to talk a little bit about lattice-based cryptography, which is a candidate and an option for post-quantum cryptography. And then I'm going to talk about a little bit of background about machine learning, or AI, which is my current research, and to show how AI systems can be trained to attack lattice-based cryptography. And so this is interesting because in the cryptographic community, we're now talking a lot about post-quantum cryptography. But what this talk is introducing is the fact that we need to also be thinking about post-AI cryptography. So what can AI do in the realm of mathematics? So there's a whole burgeoning field, which is AI for math, which is part of the more general field AI for science. And I would say AI for cryptography is the work that we're introducing here and I'm talking about today. And that's yet a smaller subsection of the broader field of AI for math. So there are actually new workshops at many of the big conferences in both machine learning and cryptography these days, which are focused on AI for math or AI for cryptography. So it's kind of a very, very new field. Okay, so let me start talking about lattice-based cryptography. So current systems for lattice-based cryptography rely on what is called the learning with errors problem. And this is a problem which is formulated in a lattice of dimension n. So n is an integer. Let's just think, so you have a ballpark idea of a dimension n, which is around, starting at like 256. It's usually taken to be a power of 2. So 256 is like the smallest lattice you should be thinking of. But for other examples, which we'll talk about later, just think about n from 256 up to, let's say, 512 or 1024 or even larger. So rather large dimensions. So what you see up here in the right-hand corner is a silly little picture of a lattice, these blue dots in the plane. This is just dimension 2. So this is a silly lattice, which is not at all appropriate for cryptography. The dimension is way too small, but it's just dimension 2 is the only thing I can draw on my slides here. And so you have, if you represent a lattice through dots in the plane, that gives you an idea. In general, you should think of a lattice is just a discrete linear subspace of Euclidean space. So think of n-dimensional Euclidean space, and then think of some vectors, let's say n linearly independent vectors in that space. And just for simplicity, just think of them as having integer coordinates, and then think of all integer linear combinations of these vectors. So these vectors form a basis for your lattice, and the lattice is just this discrete linear subspace of Euclidean space. So once you have a lattice, here's the hard problem, the supposedly hard problem, learning with errors, that is used for the foundation of the security of these crypto systems. And that is, given a secret vector, so S is a vector of length n, and given a random vector A, in fact, a lot of random vectors A, also with n coordinates, if you look at the inner product of A with S, and then you take and you add some small error vector. So the entries of the error vector, or of the error, should be sampled from a Gaussian, which is very narrow. So the entries are very small, very close to 0. And then you take this whole thing and you take it mod Q. So you get this value B. And the hard problem in learning with errors is that if you are given many pairs, A, which is a random vector, comma B, which is this secret inner product plus noise, that you should not be able to learn the secret S just from seeing these noisy inner products. So that's why it's called learning with errors. If you have a bunch of vectors like this, A, and then you're given this kind of signal or extra information, B, which is the noisy inner product of these vectors with S, that you should not be able to learn S. So that's the hard problem, LWE, learning with errors, that we'll be talking about today. So the high level idea of how this is relevant to cryptography, how is this used in cryptography, is that encryption adds noise to a kind of a secret inner product. So this is an example of a kind of typical strategy in cryptography, which is that encryption is accomplished by blinding a message. So you have a message and you blind it with, for example, like a one-time pad. That was a classical system that was used, 100 years ago or so, where a random one-time pad is generated each time, and you just take your message and you blind it by adding this one-time pad. So this is a little different because you're actually adding something that actually has an algebraic structure. So you're adding this basically secret inner product with noise to the message to blind it. So then decryption can be accomplished because if you're given the random vector A, and you know that, so if you have the secret, if you know the secret, so this is symmetric key encryption, you would take A and take the inner product with S, and you would subtract it. And then what you would have is your message, but just with a little bit of noise. And so the way we set it up, the encryption is set up so that just through actually rounding, if the error is not too large, you will actually get back your message. So the hard problem, if you don't know the secret, is to basically kind of decode noisy vectors. That is, to be able to either find the closest lattice vector in a space, or more generally find the shortest vector in a particular lattice. That allows you then to decompose things and make it easy to recover the message. So the hard problem here in this space, the easiest one to state is, given a lattice, to find the shortest vector in the lattice. So some of the attacks are based on, for example, what's called the unique shortest vector attack, USVP attack, is based on constructing a particular lattice, and then the algorithm, in order for the attack to succeed, you need to find the shortest vector, the unique shortest vector in that particular lattice. Now, there are other attacks which are require you to find a relatively short vector in a lattice, like the dual attack or a decoding attack. So that's the high level idea of LWE. And again, you should just think of it as a lattice as being given by some, set of vectors, which generates the lattice, which is the basis. And one way of thinking of the shortest vector problem is that if you have a very good basis with short vectors, it's easy to see what the shortest vector is. But if you have a bad basis, which are much longer vectors, which are not necessarily as orthogonal, they're kind of skewed to each other like this one, or imagine much, much longer vectors where the endpoints are, halfway around the world, then you'll have a harder problem to solve to find the shortest vector. Now, note that these pictures are very misleading because in dimension 2, this problem is not hard at all. So we have what you call the Gram-Schmidt orthogonalization process, which you just project one vector onto the next. So you can imagine in this picture just projecting B4 onto B3, and then kind of orthogonally projecting and then subtracting. And so you can do this in a larger dimensional lattice to get shorter vectors from the original basis vectors. And this is basically the idea of the LLL algorithm. So you pairwise take two elements of the basis at a time, and you project one onto the other and subtract. And so you can reduce the kind of the length of these vectors in the basis kind of pairwise. And so that's the idea of LLL. And in general, this Gram-Schmidt orthogonalization works very well in dimension 2. So dimension 2 is not a good example for cryptography. It's not a hard problem. So just to give you some idea of the concrete parameters here, as I mentioned, the dimensions could be anything starting at the dimension 256 up to 1024. I mentioned that the inner product plus noise is taken mod Q, so you have some modulus Q. You should think of this as basically because in cryptography, we need to implement these systems on a computer. So things need to be represented with a finite number of bits. And so we have this Q is essentially, tells us kind of what our alphabet is and makes the problem into a finite problem. The error vector, as I mentioned, the error in general should be sampled from Gaussian with some small standard deviations. So it's the error is always something small. And then the secret vector is something which is sampled from various distributions. So you first have to specify what is your secret distribution. So the safest thing to do is to sample the secret randomly mod Q. So it would be a uniformly random secret mod Q. And that would be the safest thing to do. But that's not what's done in practice for the most part. So for efficiency reasons and also even functionality, the secret is often sampled from a binary distribution or a ternary distribution or a small distribution such as the error distribution, which is Gaussian, or even what's called a binomial distribution. And so in binary, for example, that means each entry, the secret vector has n entries, and each entry is just a 0 or a 1. And if we are sampling from the binary distribution, then the Hamming weight just means the number of ones. So an even riskier assumption is to assume that the secret is sampled from a sparse binary distribution. So sparse means it doesn't have very many ones. So the number of ones is just the Hamming weight. Surprisingly, there are a number of proposals to use sparse binary secrets where the Hamming weight is extremely small. Like, for example, Hamming weight equals 64, even when the dimension of the lattice is in the tens of thousands, like 2 to the power 15. Okay, and finally, the last parameter to consider is the number of samples that the attacker gets to see when attacking this lattice. So what I wanted to do is to emphasize that, first of all, when you first think about this problem, you may not realize that there's plenty of examples where this problem LWE is just not hard. So for example, if you take Q to be too large compared to the dimension n, you can just use what I described, the LLL polynomial time algorithm, which runs in roughly n to the fourth times log Q squared roughly, to find the secret S. So in general, as Q gets larger, the problem gets easier from the lattice reduction point of view. So that might seem a little bit counterintuitive, but it's because when you figure when you try to figure out how short of a vector you need to find in order to implement one of these attacks, it's a really relative to Q that you need to find a short vector. And since the short vector finding algorithms are basically operating, over the integers or in characteristic 0, when it doesn't really matter to the algorithm, like whether, Q is large. And if Q gets large, it just makes the problem easier because it's a relatively larger vector that you can find, which will still break the system. So that's a counterintuitive thing here, which is that as Q gets larger, the problem gets easier. So if you make Q too large, LLL is a polynomial time algorithm to break LWE. So what you have to do is think about what size Q you should use. And in order to do that, what historically in the last 2 decades, what the community has done is to try to estimate the running times of different attacks in order to estimate how those parameters should be set. So for example, in the 5-year NIST competition, the 2 lattice-based schemes that were standardized, one for key exchange, Kyber, and one for signatures, the Kyber was set to have dimension essentially 512 or 768. It's basically, it's a special case of LWE where the lattice has a ring structure, or I'm sorry, there's a ring underlying the definition of the problem, which is a cyclotomic ring in dimension 256. So it's a 2-power cyclotomic ring. And then there's a module structure, either a module of rank 2 or 3 on top of that. And so it's an example of module LWE. So the dimension of the resulting lattice is essentially 512 or 768. And the size of the Q, the log Q, that's is roughly 12 bits. So it's pretty small. It's 3,300 something. And the secret distribution that's used is a binomial secret distribution. So it's small. It's not quite Gaussian, but it's very small secret, but not exactly sparse. Only 37% of the bits of the secret are 0. Whereas homomorphic encryption, which is another application of lattice-based cryptography. So the homomorphicencryption.org community, which I co-founded in 2017, published a homomorphic encryption standard in 2018. So it's been around for 5 years now, which standardized homomorphic encryption parameters for lattices, starting with dimension n equals 1024 and varying powers of 2 up to the power 2 equals 2 to the, or n equals 2 to the 15 or n equals 2 to the 16. With larger log Q are allowed, which is good for allowing more information to be packed into ciphertexts, and the different secret distributions that were standardized included binary, ternary, Gaussian, and random secret distributions with different security levels depending on the secret distribution. But in homomorphic encryption applications, the error distribution is assumed to be rather narrow. So sigma equals 3.2. And the sparse secrets are not standardized for homomorphic encryption, but they are proposed for use in practice, like the case Hamming weight equals 64 that I mentioned. So just to give you a high level view of what the classical attacks on LWE can achieve. So I mentioned already LLL for lattice reduction. That is kind of pairwise reducing lattice basis vectors by projecting them onto each other. And generalization of LLL to what's called BKZ actually projects basis vectors onto higher dimensional sublattices generated by K of the basis vectors. So we'll call K the block size. And so BKZ works by, you shorten the basis vectors by kind of projecting them onto smaller subspaces. And so FPLL is a software implementation of these, and which now includes BKZ 2.0, which includes a lot of different improvements to make BKZ run faster. And so it had a lot of different contributors over time, including those listed here. And using all of these different lattice reduction algorithms, Albrecht, Player, and Scott in 2015 developed an estimator called the LWE estimator that can be used to estimate the security of different lattice-based schemes, the LWE-based schemes, by estimating, not actually running the attacks using these lattice reduction systems, but by estimating them, how we think they would perform in practice. So unfortunately, there's actually very few kind of benchmarks for concrete secret recovery attacks. I should have mentioned on this slide, there's the Darmstadt lattice challenges, which have been around for many years. But unfortunately, they're not that relevant for the lattice schemes that have been implemented in practice, because as I mentioned here, in practice, a lot of the schemes are using a different secret distribution, so not a random secret, and using a small error distribution, and even sometimes like sparse binary secrets. And none of the lattice challenges and the Darmstadt lattice challenges, none of them are using any of those parameters. So we really have a lack of concrete results to compare against. Going back to 2015, I did some work in this direction with Kim Leine, and in 2019 with Lin Chua and Hao Chen and Young-Soo Song, so providing some concrete secret recovery attacks to compare with, including just using LLL and then using BKZ and recovering secrets at different parameter sizes. So it gives you kind of an outer boundary of where you should set parameters that are certainly insecure. Okay, so now I'd like to kind of just summarize this last part of my talk and move on to the machine learning part of my talk. So this was the more algebraic side with a little bit of number theory coming in the cyclotomic, 2-power cyclotomic rings underlying ring LWE. But so just to summarize what I've said so far is that post-quantum cryptography is relying on new kind of algebraic systems, algebraic or number theoretic systems, for which we don't know any polynomial time quantum attacks. So lattice-based cryptography is believed to be quantum and classically secure if you select the parameters carefully to avoid the lattice reduction attacks that we know about. And the underlying hardness assumption, as I described, is this learning with errors assumption. It was first proposed by Regev in 2004, so it's roughly 20 years old. And the hardness assumption is stated, rather simply, which is that given a bunch of noisy inner products with a secret, the challenge is to learn the secret. And so then I've kind of summarized also the state of the art with using classical attacks based on lattice reduction to attack these systems and setting parameters based on best known lattice reduction attacks. So now to the second part of my talk. So the question is, could we use a different attack paradigm? So I had actually long thought before going to Facebook Meta 2.5 years ago, I had long wanted to look at using machine learning to attack these learning with errors problems, because machine learning is good at learning from noisy data. So at a high level, let me just describe what supervised machine learning looks like. What you're given a lot of labeled data, so we'll call that training data. We're going to train a model. So the first stage of machine learning is training, where you should try to use some mathematical process to derive a function, or what we're going to call a model, from the training data. Then once you've learned the model, then you use the model in a prediction stage to make predictions on new data. So we often call the training stage, we have training data that we train the models on. Then we have test data to figure out how well the model is doing. And once the model does pretty well on our test data, we might stop training. And then we would go to the prediction stage where we use the trained model. So, for example, you're probably using machine learning models every day in systems that recognize your voice, such as Siri, recommender systems that recommend, movies or other things like that, or more serious applications in finance or health, detecting fraud or detecting different kinds of genomic let's call them genomic flaws, or blanking on the name for genomic mutations, sorry. And so all kinds of different applications of predictive modeling in the real world. So now let me just kind of give an example, just so you can kind of think more concretely about machine learning. This is in a health setting. This is one of the first applications that I worked on long ago. So imagine you have a bunch of data here. So each row, you could think of this as a vector. So the data needs to be turned into some kind of mathematical formatting. Think of each row as a vector here. So these are all measurements of a tumor. Imagine like a liver tumor. And each column represents some kind of characteristic or attribute. And then there's some amount of precision that's been decided ahead of time, and the measurements are entered with that amount of precision. And then each of these rows, imagine it comes from a different patient, and each one has a label. Was this tumor considered to be discovered to be benign, which we label with green, or is it considered to be malignant, like cancerous, so labeled with red? So this is an example of labeled data. It's a relatively small dimensions here, dimensions somewhere around 15 or 20 entries in each vector. And so what we're going to do is to develop a very simple model here. This is kind of the simplest machine learning model you could think of, which is a linear means classifier. We have binary labels, just 2 different labels for this data. And the idea is that you compute the mean vector for each class. And then because you can group the classes because you have the labels. And then you compute the difference between these means and compute the midpoint and define a hyperplane between the means, which basically separates the 2 classes. So again, this picture is kind of ridiculous because I'm drawing a 20-dimensional data set in 2 dimensions, but I'm doing it just so you can kind of visualize. Imagine that the green labeled data points are clustered over here, and the red labeled ones are clustered over here. And by finding basically the hyperplane that separates them, you're defining what I'll call a decision boundary. So the whole machine learning task is really to find this decision boundary. And then what you would do is on a new vector that comes in, you would just decide which side of the decision boundary is your vector on, and then make your prediction based on that. So you can see it's not an exact science, and it's an approximate science. But in particular, we have things that are much more sophisticated than just like a linear means classifier. And the general strategy for supervised machine learning, the way it works is that you're gonna, again, let's just assume that you have binary labels. You can have multi-class labels as well, but I'm not going to describe that here. The idea is that you have to define what we call a loss function, such as the least squared distance, which is going to be a sum of distances between your points and your boundary. And you're going to constantly update your boundary so that you can minimize this loss function. So this is kind of a multi-dimensional, surface that you're essentially walking around, and you're trying, which are is going to be the parameters of your kind of decision boundary, and you're trying to minimize this loss function. And when you've deemed that you've minimized it well enough, you stop, and that's your model. Your model is basically your boundary. And this process, for example, using like stochastic gradient descent, is basically multivariable calculus. So you can see this isn't necessarily the very algebraic side of mathematics, but you can see it's just a mathematical process, which is followed to learn like the simple models such as linear or logistic regression, but now more recently, much more complicated models, which kind of have many layers that iterate these processes, which lead to what's called deep neural nets, or things called transformers, which is what we're using today, in particular in the attack that I'm going to talk about. So that was like just a little section, which is kind of just explaining the background basics of machine learning. If you've taken even a basic course in machine learning, then you probably know much more than this already. But so now I'm going to talk about using machine learning to actually attack LWE. So remember the LWE problem, you're just given a bunch of samples, A, B, which is your data, and your attack goal is to recover the secret. And so what we decided to do in our first paper, in our SALSA paper, is, LWE assumes that learning from this noisy data is hard, but we found that, we think that machine learning models are actually good at learning from noisy data, and that LWE is actually a lot like a linear regression model, but it's modulo Q, unfortunately. And modulo Q makes things hard for machine learning. Machine learning is not yet very good at doing arithmetic mod Q. So that's something we're working on. We worked on it in this project, in the SALSA papers, and got it good enough to use, but we're working on that actually in my Win6 project. We're actually working on machine learning for modular arithmetic, trying to get it better. And so what we decided to do, the way that we attack the machine learning, or use machine learning to attack the LWE problem, is that we actually train a model on these LWE samples, A, B, and the prediction task that we train it to do is to predict B from A. So given a bunch of samples, A, B, we're going to train a model. And then once our model is trained well enough, as far as from our criteria, we stop, and then we use that model to predict B from A, and then doing that on particular A's that we feed to the model, we develop these cryptographic distinguishers, which can be used as an oracle to recover the secret. So that's the strategy that we developed. And we found in the first paper, SALSA, in 2022, it was published in NeurIPS, which is one of the top 3 machine learning conferences, that we could recover sparse binary secrets for very small size LWE problems. So small dimension and very small secrets, binary secrets that were very, very sparse. And SALSA, in case you were wondering, is the acronym for secret recovery attacks on LWE via sequence-to-sequence models with attention. So it's not a perfect acronym, but it's SALSA represents exactly what we're doing, which is training these particular type of transformer models called sequence-to-sequence models with the attention mechanism. And we use the attention mechanism in particular in follow-up work in Picante and Verde as an additional secret recovery method. So the ingredients of salsa are the transformer model and the secret recovery model. So I actually also like to take this opportunity to thank one of my co-authors, Emily Wenger, for a lot of these fantastic slides, including the ingredients here that you see, the onion and peppers and tomatoes. These are the ingredients of the salsa attack, which is the transformer model, training the transformer model, and then using our distinguishers to do secret recovery, and then to verify whether we have actually found the secret. Without knowing the secret, we have secret verification methods. The way that this works is the salsa, the interesting thing is that salsa can actually recover secrets even when the model just starts to learn. So we actually don't need high accuracy on our task, which is given A, predict B. It doesn't have to be predicting B very accurately in order to be able to recover secrets. So these are some graphs of the test loss and the test accuracy, just to kind of get some idea. And what you can see is the test loss. So again, let me remind you, what do we mean by test loss? So we will have trained a model on a certain amount of data so far, and then we'll be testing it on some data that the model hasn't seen yet. And we're kind of looking to see when does the loss really drop here. And when, as you can see, the left hand, the y-axis, those numbers don't necessarily mean much to you, but what does mean a lot is the graph that shows when the loss has dropped. So in dimensions, the different colors represent different dimensions from 30 up to 128. And the x-axis here is just time. So the amount of time that the model had been trained. We actually use, you might wonder, why is 128, which is red, why did the loss drop earlier for 110 and 128? And those were just kind of a fluke, because we were using, I think, bigger models there. And so they learned faster. But in general, what you can see is that at some point the loss started to drop. And so now if you go down to this bottom graph, and you can see with these dotted lines, this was roughly when the loss started to drop. And at roughly those points, you can see the test accuracy started to really shoot up in these different dimensions. So the interesting thing to note here is again, the x-axis is essentially time. It's the number of training epochs that were performed. But the y-axis here is a little bit more understandable. It's accuracy. So given A predicting B to within like a small error, and we only need somewhere around 25 to 30% accuracy. And you can see that is right around the point when these curves start to go up, is about the time when we start to recover secrets. So we don't need to train these models to get like 96% accuracy or something, which is very typical for lots of machine learning applications in the real world. We're already recovering secrets when the models have been trained just to like around 30% accuracy. And there's also a bit of a theoretical reason for that. Okay, so in the time remaining, I'd just like to talk a little bit about some of the improvements that we've made to salsa since, a year ago, since the original salsa paper. So we have both the salsa picante and the salsa verde papers, which are appearing in top security and machine learning conferences this year in 2023. So initially, we had secret distinguishers, so the direct and the distinguisher methods. And now in Picante, we have an additional secret recovery method, which takes advantage of the cross-attention mechanism in the models that we've trained. And just to give you an idea of how the distinguisher works. So imagine you have a secret S, which is a binary secret. So it's got n entries, and their entries are just zeros or ones. And imagine that you have you're just looking at one bit of the secret, the ith entry, the ith bit. And a sub I corresponds to the coordinate of the vector, the random vector A. So it's random mod q. It could have some rather large entry. And then if you look at B is the inner product of A with S, and then just adds like some very small error. And so what B is basically doing is it's a subset sum. It's basically adding up a whole bunch of entries of A, and then adding just a little bit of error. So you can think of the real problem here is it's a subset sum, and you want to know which of the bits are getting added together. So if you look at, let's let A sub C be the vector A, but with a rather large constant C added to it. And remember, all of these operations are being done mod Q. So if you have that the bit SI was 0, then when you looked at your prediction from your model on the vector A sub C, you would expect it to be similar to the prediction for the vector A, because you added a large constant to the ith entry of A, but that got multiplied by 0, so it shouldn't have made much of a difference. So if SI is 0, then you expect the predictions for A and A sub C to be relatively similar. And so these are things that can be kind of measured statistically, and you can kind of get an idea why we don't really need high accuracy. One of our initial methods was to actually compare F of A sub C with B, but B being the true second coordinate of your sample, A comma B. But in fact, that wasn't very helpful, because it doesn't even need to be close to B. It doesn't matter if it's close to B. It just matters whether there's a big difference between F, the model's prediction on A, and the model's prediction on A sub C. So that's the idea. That's a high level idea of the distinguisher. And in fact, as we've scaled up to larger dimensions, the distinguisher is winning as the best secret recovery method. And we kind of understand the reasons for this. In smaller dimensions, we had these other techniques, such as the direct secret recovery, that worked pretty well, but it's not scaling well to higher dimensions. Some of the key limitations of SALSA were that we needed a lot of LWE samples. So that parameter I mentioned in the beginning, which was M, was the number of LWE samples. And we needed 4 million LWE samples, which is a lot. And we could only make it work in small dimensions to begin with, and relatively low Hamming weight for binary secrets. And so in the follow-up work this year, the Picante and Verde papers, you can see that we've been able to eliminate many of these limitations, and it's much closer to attacking real-world systems, or at least being a method that should be considered to think about the security of real-world systems when you have special choices like sparse binary secret and small error. So, for example, if you look at this first row here, SALSA, which required 4 million samples and had small Hamming weight and small dimension and binary secrets, you can see that in SALSA Picante, we're able to reduce it to only needing 4n samples, 4 times the dimension. We can attack much higher Hamming weights, for example, Hamming weight 60 and higher dimensions, dimension up to 350 binary secrets. And if you look at the third row, Verde, you can see that, again, using smaller number of samples, we can reach even higher dimensions, such as 512 with Hamming weights something like 63, and we can attack binary ternary Gaussian secrets. Now, the thing that you're not seeing on this chart here is how big was log Q. So what we do is we take the best log Q that have been attacked with previous methods, like, for example, as mentioned in our 2019 paper, using BKZ and lattice attacks. And we look at the log Q for which we could recover secrets, and then we choose smaller Qs than that. And so starting to form benchmarks for those smaller Qs and these binary secrets with, and this is actually not even particularly sparse compared to the sparsity used in homomorphic encryption. For example, we're already able to do Hamming weights roughly what they use for much, much larger dimensions, like n equals 2 to the 15. So Hamming weight 63 or 64. But the key thing that you're not, and we're also able to do binary ternary Gaussian secrets. So you're getting very close to Kyber in some sense here, because you've got dimension 512 and you've got small secret. But the difference with Kyber is that here we have Hamming weight only 64. So the sparsity is way, way larger than what's assumed in Kyber. Kyber is assuming around 37% zeros, and we're assuming basically somewhere around, well, whatever, 1 over 2 to the 9 minus 6, 2 to the 3. So about 7/8. We're assuming 7/8 sparsity here, which is much larger than 37%. So we're not attacking real world systems here. So just to give you a kind of a data point to compare to, we would have to have much more general secrets, not so sparse, and also in some cases much smaller Q. Okay, so I don't have that much time left, and so I'm going to skip over some of the details of how we have achieved these improvements in Salsa Verde and Salsa Picante. And we have been able to recover, as I mentioned, ternary and Gaussian secrets. But I'd like to spend kind of the last couple of minutes on comparing with what are called the unique shortest vector attacks. So the interesting thing here is that I only have concrete comparisons to show you from our, especially our Verde paper, for n equals 256. And that's because in our paper where we show attacking n equals 350 and n equals 512, we're actually not even able to get these USVP attacks to run. Now, there's a lot of issues with getting these to run. One of them has to do with the amount of precision that you need to make them run. And so people that work on this full time can tune these things better than we can, and may be able to get the higher dimensions to run to get those comparisons with our times. So we're actually comparing only for n equals 256, where we're able to run the unique shortest vector attack. But as we had in our original version of our Verde paper from May, you can see that actually in these smaller dimensions, there are better attacks that are possible, such as the meet in the middle attack and hybrid attacks, which are quantified via the LWE estimator. So we have those LWE estimates in our Verde paper from May, which give the kind of rough attack times using these other attacks. But we just didn't have the time and the effort available to implement all these other different classical attacks to compare to. And the interesting question is, those are not necessarily the best attacks for scaling. So we're focused on using these AI methods to scale up to higher dimensions because our approach is not really limited by dimension the way others are. So it's kind of an interesting open question how these things will scale the whole range of different classical attacks and how they will scale to higher dimensions. So this chart that I'm showing you here on this slide is just for n equals 256, which is the smallest dimension that we give in the Picante and Verde papers. So as you can see on the left-hand side, the first column is the log Q. So as I mentioned, the problem gets easier as log Q gets bigger. So log Q equals 20 are the kind of easier instances, and log Q down to log Q equals 12, and that is, for example, what's used for Kyber is log Q 12. N equals 256 there, but remember it's a module LWE, so it's actually a 512 or 768 dimensional lattice. And if you look at log Q equals 12, we're not able to get the USVP attack to run or to recover any secrets at all. The total attack time for using the AI methods is around 4 to 5 hours for log Q 12 and 14. And as the log Q gets larger, interestingly, our timings get a little bit larger just because it's just more expensive to work on larger Q, but they're not that much larger. They're still anywhere in the range of basically like 10 to 15 hours for all of these things. So what this you compare with over here is these USVP timings, which can vary widely, which that in itself is a little bit scary. It shows that there can be a very kind of random element to whether the secret is found or not here. Like, for example, log Q equals 20, one instance found the secret in 76 hours, where another one found the secret in 401 hours. So wide kind of variance in the attack time for USVP here. But I want to call your attention to this column here, which is that just to be fair, I need to emphasize the fact that our attack pre-processes our data with, in some cases, thousands of machines. So in terms of the amount of compute resources that were used, you could say that our AI method takes more resources than the USVP attack. But our method can be parallelized because all this pre-processing can be done in parallel. And so in terms of time, it can be like, for example, for log Q equals 12, that we will only take, an hour and a half to prepare the data, and then just 2 epochs of training and running the distinguisher and the verifier. And so the total attack time would be like 4.5 hours. But that's keeping in mind that we did use like thousands of machines to pre-process this data. Now, so in fairness to comparisons with other approaches, this is a snapshot of our work as of May. It's actually very easy to improve the kind of pre-processing step, and we have done that since then. So our pre-processing takes much less time and many fewer machines now than it did then. And also, there's a number of other aspects of lattice reduction, which when there's a new best paper at Crypto this year was called the Flatter software, which also improves lattice reduction. And those lattice reduction improvements directly translate into improving our methods as well. So anything that improves classical attacks will essentially also improve our AI attacks. Okay, so I'd just like to close with a little bit of a few comments on future work. So one of the things we're working hard on is to improve the model's ability to learn modular arithmetic. As I mentioned, we've already been decreasing the pre-processing compute time and resource requirements, and methods for concentrating the distribution of the data that we learn that we use to learn from. So in summary, in this talk, I've kind of focused on post-quantum cryptography, or what we might soon be calling post-AI cryptography. We want to consider algebraic and number theoretic systems for cryptography for the future, where we might have a quantum computer. So we need to avoid the systems that we have today, such as RSA and ECC, once we have full-scale quantum computers. And we need to at least consider both quantum attacks and AI attacks on all of these systems. And so in this talk today, I've showed you our new approach to using AI for attacking lattice-based cryptography, or the learning with errors problem, and shown kind of the state of the art and some of the challenges that we face with this particular approach. So thank you so much for your attention.
Okay, thank you very much, Professor Lauter, for this very, very interesting talk, as usual. So, are there any questions for Professor Lauter?
Yes, hello.
Hi.
Hi, Christine. Thank you for your interesting talk. My question is, what are the advantages of using machine learning like transformers in attacks such as SALSA compared to traditional cryptanalysis techniques?
So I think let me go back to this slide. So here I was comparing the machine learning attacks with the traditional attacks, but we only have the timings for comparing with the unique shortest vector attack. I didn't include the slide, which is in the paper, which gives the estimator timings and which method is the best. So going back to this slide here, let me see if I think I had a summary of some of the classical reduction attacks. So I think that you can summarize the advantage, or at least one of the advantages, in the following way. The unique shortest vector attack requires you to correctly find the shortest vector in order to get the secret. If you don't find the shortest vector, you don't get the secret. That's an easy way to think of it. Some of the other attacks, classical cryptanalysis, such as the dual attack or the decoding attack, you just need to find a small vector, but the vector needs to be small enough. If it's not small enough for the parameters that you've chosen, the Q, the N, Q, error size, all of that, then again, you will not find the secret. So that means that when you're running lattice reduction, which can be a very, very, very costly process, as you could see from my charts, taking, like 500 hours or something like that, or much, much more. I mean, you can run lattice reduction. We literally ran it for months in some cases, waiting to see if we could get the secret. And the problem is that if it doesn't get the vector which is short enough, then it doesn't succeed. Whereas in our pre-processing stage, where we're using lattice reduction to pre-process data, it's not about finding a short vector or a vector which is short enough. It's about changing the distribution of the training data. So as soon as you start processing the data, you can already start harvesting it. And so you can already start learning from the data immediately. You do not need to wait for lattice reduction to terminate in order to run the attack. So that's like at a high level, the kind of a big advantage of our system. Our system is also pretty flexible in the sense that maybe we don't even need lattice reduction at all. All we need to do is to concentrate the distribution of the data. So it doesn't necessarily need to be short vectors. So there could be another method which has nothing to do with lattice reduction, which would help us to concentrate, basically reduce the standard deviation. And another kind of final point that I'll make in terms of comparison is that we are able to recover secrets and attack these systems, even though our AI, our machine learning models are very bad at modular arithmetic. So if we can get our models to be better at modular arithmetic, then it's going to remove most of the kind of limitations and restrictions that we see on, small Q, small Hamming weight, all of these things. And it already scales very well with dimensions. So that's what we're really aimed at it now, is really improving machine learning ability to do modular arithmetic, which also has implications for other cryptographic problems such as Diffie-Hellman and RSA and things like that. So once we can do better modular arithmetic, we can use AI throughout public key cryptography and consider the implications there.
Thank you very much.
Thank you.
Okay, so Marlicha Sandoval Miranda, who is one of our organizers, shared these questions of the PhD student, Oscar Casimiro, from the Universidad Autónoma Metropolitana. So the question is the following. Question is, are attacks on crypto systems using machine learning techniques more effective than common attacks, such as the el algorithm?
So this slide here is listing some of the other common attacks. So LLL is kind of the basic, and then BKZ is a more complicated version of LLL. BKZ 2.0 is an even better version. And so, just two things that I mentioned on this slide I want to highlight. FPLLL is an open source, openly available implementation of these things. So you can just search for FPLLL and you can find these algorithms implemented. And the LWE estimator from Albrecht et al. Estimates these schemes. So those are the things that you use to compare, to kind of describe and compare the existing classical attacks. And then this slide here is just showing our comparison using BKZ 2.0 as implemented in FPLLL. So these are not our custom implementation, but we're running the attacks on the same cluster, on the same hardware that we run the AI attacks. So we're trying to compare like apples to apples by running the systems, the two systems on the same cluster. And then, so this slide gives the timing comparison. So you can see that with comparison to the unique shortest vector attack, that in terms of timing, that we're much better than the USVP attack. But as I mentioned, we used more resources because we did some parallelized pre-processing ahead of time using lattice reduction. And then, as I mentioned, we do not have the comparison in small dimension with other things such as meet in the middle, which are predicted by the lattice estimator to be faster. But in higher dimensions, where we have our AI attacks working, like dimension 512, USVP is predicted to be the best attack, not these other ones you meet in the middle. So for these particular scenarios, which is, remember, we're attacking small, sparse secret, binary, small in general, but binary sparse secret in this case. So that means H here is the Hamming weight. So that would be like in dimension 256, that would be like saying you have 25 ones. And so then we're comparing with the USVP attacks on those kind of small sparse secrets. But USVP attacks, remember, USVP attacks can be used to attack general secrets, like random secrets, uniformly random secrets, whereas our attack so far is only working on sparse small secrets, sparse binary secrets, or ternary or Gaussian.
Okay, thank you very much. So it's very interesting to see that PhD students from Mexico are very interested in your talk, Professor Lauter. So now, okay, so just let me say thanks for your very interesting talk. Thank you to all the participants. Now I will pass the chairing permission to Yuriko Pitones and to Marlicha, who are in charge of this conference. Maybe she will provide us information about the conference in the next few days. So thank you.
Thank you so much.
Thank you so much, Professor Christine, and thank you, Duan, for the presentation of this talk. And we are done for today. Thanks everyone for coming. I hope you have enjoyed the talks, and we are waiting for you tomorrow to continue with this conference.
Bye-bye.
Bye. Thank you.